Hello. Saurabh, good morning, everyone. I hope you all had a restful night and are ready for another exciting day at ICNACT 2024. My name is Hashita Srivastav, and I'm delighted to welcome you back for day two of our conference. Yesterday, we had an incredible start with the inaugural session to parallel sessions to mesmerizing cultural events. It was inspiring to see many brilliant minds come together to share knowledge and innovate. Today, we have another fantastic lineup for you, for which I would like to welcome our session chair for this session, Dr. M. Mursaleen. Due to some unavoidable reasons, Professor Ravi P. Agarwal is not present with us, so I request our session chair to introduce our next invited talk.
Thank you very much. So, let us start today's session. And unfortunately, our first speaker, Professor R.P. Agrawal, is not feeling well. He has some health issues. So, we start with our second speaker, Professor Wahid Rumi. Professor Rumi is an assistant professor at Azerbaijan Shahid Madani University, Iran. He obtained his PhD from Iran University of Science and Technology. His research interests include differential equations, control theory, mathematical biology, nonlinear analysis, and dynamical systems. He has published several books on calculus, probability, and statistics in Persian language, and he has also published a number of research papers in reputed journals. The title of his talk is Analysis of some models containing insurance parameter for infection diseases via some fractional derivatives and numerical simulations. So I request Dr. Rumi to please come and give your talk. Thank you very much.
Hello, everyone, and thank you for being here to hear my talk. I would like first to thank the organizers that invited me to be one at this great event. Before starting my talk, I would like to dedicate this talk to great mathematician, my brother M. Morsalin. Next, please. Yes, you see my uh, title of talk. I'm going to talk about a system of differential equations that describing an infection disease containing some control parameters. One of the control parameters uh, may be maybe insurance parameters. Next, please. In this talk, we will consider an uh, dynamical system of fractional differential equations, and we want to use optimal control methods to find the optimal control for the uh, controlling the disease. And numerical simulations also uh, we will done, and most cost effective and efficient optimal control will be found for the system. Next, please. Here is the flow chart of the system, and in the next slide we will see the system of differential equations. Next, please. First of all, I define some differential operators. Let be continuous and differentiable function on an interval. The fractal fractional derivative in Riemann-Liouville sense is defined as follows: the relation 1-1. But there are three special cases. That the first one is 1-1, and the second is 1-2. And next, please. And the third one is the relation 1-3. The associated integral definition is come in definition 1-2. There are definitions of the corresponding integral of equations. Next, please. We consider an SEIR V epidemic model that 4 compartments are related to humans, susceptible people, exposed people, infected, and recovered. And the last one is the quantity of virus concentration that we denoted by V. Relation 2-1 shows our dynamical systems. That parameters are described in the next table, please. And we have to consider initial conditions and positively invariant region for our system. Next, please. The parameters that are in our system are described here. For example, the first one is the rate of versus or recurrent of rate. The second one is natural death rate, for example. The blue one, the last blue one, is mortality rate of people with the disease. And some other parameters are also here. The next, please. One of the most important parameters in mathematical biology is called reproduction number. Reproduction number shows us, on average, how many people can be infected with one person in duration of infection. If R0 is less than 1, it shows that the infection, the disease are our control and will be die out. And if it is greater than, it means that the disease will stay in the population. Next, please. First, we want to calculate the reproduction number R0 or not. To calculate this one, we use next generation method, next generation matrix method. First, we have to find the disease-free rest point that we calculated E0, as you see here. In order to use next generation method, we have to divide infected infection compartments with others, as F and V you see here. And next, please. After dividing the compartment, we have two matrices F and V here. Then we calculate Fv minus 1 if Fv inverse and R0 R0 is the spectral radius of this matrix. If we calculate that one, we saw that R0 is equal to that last relation. Next, please. Besides our disease-free equilibrium, we have another rest point, that endemic equilibrium, that we have calculated like this E star, and that components are you see as here. The next, please. In these two theorems, we have proved the local and global stability of the disease-free equilibrium. If R naught is less than 1, then disease-free rest point is locally asymptotically stable. In order to prove that, uh, we we prove that all eigenvalue of the Jacobian matrix at E0 are negative or have negative real parts. I omitted the details of the proofs. In the next theorem, we showed that if R0 is less than 1, this free rest point is globally asymptotically stable. In order to prove that, we have to find, which is not easy, we have to find a suitable Lyapunov function and show that its derivative along the solutions of the system is negative. I also removed the details of the proofs. Next one, please. In this section, we proved the existence and uniqueness and positivity of the solutions of the system. We defined 5 functions, y1 and y5. The proposition says that the functions that we defined above satisfy Lipschitz conditions if phi j, phi 1 to phi 5 satisfy the inequality between 0 and 1. The next, please. This theorem, theorem 4.2, proves us if z is equal to maximum phi j, if it is less than 1, we have at least one solution for our system. In the next theorem, if the inequality for 2 is satisfied, then the solution with any initial conditions, positive initial conditions, is unique. And next, please. R0 sensitivity is considered in the next section. I said that R0 is a very important parameters, and one is its threshold. And we want to know that which parameters of our system can increase or decrease the R0. It is very important for us. We calculated the derivatives or R naught with respect to the parameters and showed that R0 increases with these parameters and decreases with these parameters, because always we want to decrease R naught to control the disease in the population. Please, next one. Uh, as you saw in the previous slides, we had 3 control parameters in our system: U1, U2, and U3. The first one is awareness via media. The second one is vaccination, and the third one is therapy. I told you one of these parameters can be replaced by insurance parameters that we are working on it, and I think we can get good results in a few, for example, a few weeks. Our goal is to reduce the number of infected people and also to reduce the costs related to these three controls. The objective function is defined as follows. The aim is to find the control function such that minimize the objective function. Next, please. In order to do that, we consider the Lagrangian and the Hamiltonian function, and we can uh, we can calculate the Hamiltonian function by replacing the parameters or equations from our system. The next theorem shows that assuming that U1 star, U2 star, and U3 star are the given optimal controls, and this is the solution of the state system, there are adjoint variables like this that satisfy the next conditions, please. These conditions and also transversality conditions, and we prove that the optimal control U1 star, U2 star, and U3 star are as follows. So we can find the optimal control for our disease. In order to prove that theorem, we apply convergent maximum principle that that these functions, the optimal control can be used to solve the optimal control, must satisfy these equations. As a result, optimal control can be calculated like this. Next, please. Also, optimal control can be expressed in the following from after exerting the boundary condition on the controls. Next, please. In the next section, we have numerical simulations. We applied numerical method to find numerical solutions, and we want to compare real data with our results. Utilizing Newton polynomial approximation, we can have the following method to simulate our solutions. Next, please. Corolla in Yemen in recent years, which caused by bacterium Vibrio-Corolla, Yemen has recently experienced the large outbreak of Corolla in the world's history. We want to compare our results with real data of this disease. Of course, this can be replaced by other data from other disease. We show that it can be observed that the data aligns well with the model for the fractional case with P and Q equal to 0.85. Then there are the real data, and the blue one is related to P and Q that are the fractional and fractal orders of the system. Please, next one. In the next figure, applying the different value for P and Q, we show that any compartment of our system how does the classes S, E, I, R, and V from April 2017 to April 2018 will be examined. The parameters value of the one for the outbreak of Corona in Yemen are available in the next table. Our parameters for this disease are like this. Some of them are estimated, some of them are fitted, and some of them are from other references. Next, please. In this figure, we see that how the dynamics of the compartment without any control. This figure is related to infection people. You see that without control, we have 6 with 4 zeros, uh, infection cases without control. Next, please. We want to use 4 strategies to examine 4 strategies to determine the effectiveness of our control on the to reduce the corona disease. In the first strategy, the awareness via the media and the vaccination will be considered. I mean that U1 and U3, U2 are not zero, but the vaccination is removed. It means that U3 is zero. In this strategy, the changes of each classes are shown in the next figure. In this strategy, with P and Q with these values, we see that the infected people are reduced to 6,000. And the next strategy, we consider the awareness and the vaccination are not zero, and the second one is zero. In this strategy, we see that the infected people is a little more than the previous one, but very less than the case that without any control. In the next strategy, we use U2 and U3 not zero, and the U1 is zero. In here, we see that again, the infected people are very less than the case that without control. These are other classes, susceptible people, and for example, recovered people, and the concentration of viruses in the environment. Please, next one. In the last strategy, we use all controls here. None of them are zero. All 3 controls are applied in this strategy. We see that the number of infected people reduced very well with respect to the previous strategies. Please, next one. Besides maybe sometimes applying controls, all controls for controlling a disease make many is very expensive, and we want to know that which strategy can control the disease with less expenses. So we use the cost effectiveness. We want to calculate cost effectiveness of different control strategy. We utilize incremental cost effectiveness ratio that are described here to calculate the most effective strategy. We have strategies here, total infection averted and total costs here. Please, next one. In this table, first we calculate this parameter, previous please, with this formula, please, next one. And we see that this number is greater than all over them. So we remove strategy A and do again this process. Please, next one. After removing strategy A, we calculate ICER again, and we see here that this number is again greater than the other one, so we remove the strategy C from the process, and the next one. And finally, we calculate again what that with that formula, we see that this number is greater than the above one, and so we remove the strategy B from our decisions. So strategy D is more costly and less effective than strategy B. Consequently, we remove strategy D based on the analysis outcome. We recommend strategy B to be applied for this disease in Yemen. And you see here our conclusions. And uh, I want to finish my talk with some speech here. Recently, the scientists discovered that viruses can hear and can see. What does it mean? It means that they are intelligent. They know that which time is better to attack, which time is better to be silence. This is the first point. This is the starting point that the scientists believe that these we can use these to control the disease. We can, if we could know in what frequencies viruses uh, are active, we can send that frequencies to them to be active, and then we can remove the viruses from the body. Okay, next one, please. Here are my references that are used. And next, please. Next, please. And I want to finish my talk with great sentence from a great mathematician, my countrymate mathematician, who is between six scientists that changed the world, Maryam Mirzakhani. The beauty of mathematics only shows itself to more patient followers. Thank you very much.
Thank you very much.
It's already.
Okay. So if there is any question or suggestion, please.
Hello. Uh, Thanks for the nice talk. And what I would like to ask is, given a biological phenomena, as you have considered some disease, uh, how to how to fit a mathematical model into it?
To real data,
Yeah.
we use MATLAB.
No. But I don't get all that you get from the MATLAB is just some more information. This is not a mathematical model which describes the phenomena. Given a biological phenomena, suppose there is growth of fungi or bacteria or anything, how can I fit in fit a mathematical model into it?
You mean how can we calculate the parameters of the model?
Yeah,
Yes. We have some experimental data from before,
yeah.
from the next, for example, months. We collect the data and we fit.
But that can be done statistically.
Yes, that we done
But not,
statically.
yeah,
Yes,
that is a
this is
statistical phenomena.
yes,
But
this is
that
a
is
way.
not mathematical model, meaning is like some continuous differential equation. I should be able to say that this differential equation, solution of this differential equation is giving me the phenomena described by the biological thing?
Uh, there are many papers in this area that mathematical differential equations are describing
Yeah,
the
like you
mathematical.
have
Yes.
demonstrated your fractional derivative thing.
On MATLAB or Mathematica, we can use the previous data and fit to our modeling to find the parameters, the best parameters. In one slide, I showed that our our solutions are fitted very well with the real data. After these that weighs in our um, our system. Uh, this system, I said, can be used for some disease like Crolla and some others that are the same, have the same dynamics. But if we can, if, for example, we want to use for uh, other diseases, we have to consider some other compartments or some other ways of transmission. Here I talked about a pandemic, yes, but we can apply these systems, for example, for disease like HIV, AIDS. For example, we can consider the cells of body like populations, and we can use this system to that disease too. But we have to change some parameters, some change some compartments. Yes, I can say we have to use something in some different diseases. Thank you.
Okay, sir. That means it varies up to the cell division of bacteria. So how rapidly it is infecting.
How,
The
sir?
parameters depends on that.
Yes. Parameters. We use general parameters like alpha, beta, lambda. But in case of corona or a case of coronavirus, we use the real data to estimate the parameters. If we use the same system for two different diseases, the parameters are different, are totally different. Yes.
Thank you, sir.
Thank you.
Good morning, sir.
Thank you.
Sir, such kind of problem can be applied for stochastic one or stochastic differential equation. And what could be its impact? Can you let me know that?
I have not used that stochastic, but I know that it is the one of the best way to describe the disease. And beside the stochastic, we have uncertainty theory. I'm not sure that you are familiar with it or not, but there is a bit difference between both of them. Both of them can be used to describe the diseases, but I have not used them.
Okay,
Okay,
sir.
thank you. Yes, please.
Hello, sir.
Yes.
Good morning.
Sorry.
Can I know the estimation of parameter in this model? Did you use a fractional model or classical one
Uh,
for the purpose of estimation of parameter?
I didn't understand. Please, maybe repeat.
You have shown in the parameter fitted data.
Parameters.
Yes, yes.
Yes.
Did you estimate it from the classical model on or fractional model?
Both of them are used to model these diseases, but if we want to use the previous results to predict the next results next days, it is better to use fractional system, because fractional order restore the previous data, but if you use the ordinary differential equations, just it use the current dynamics of the compartments. But when we use fractional order, the fractional order differential equations store some data from the previous days. I'm not sure I understand your question or not, or if not, we can discuss after the session. Thank you very much.
Good morning, sir.
Thank you.
Sir, in your presentation, in between, you have used some Newton polynomial.
Sorry,
Newton polynomial.
neutral.
Newton polynomial.
Okay.
So, are you using some particular degree of that polynomial, or
We use that Newton polynomial to find our numerical solutions.
what is the degree of that polynomial? Any particular degree you are using, sir?
Uh, I think we use degree 2, yes, but we can use some other degrees of polynomial.
Okay, sir. When we are using degree 2, so since it is fitted to your experimental data, so how much accurate it is, sir?
How much?
Accurate. It is accurate up to 4 decimal, or
Uh,
so is there any convergence criteria of that method, sir? It is correct up to
you mean that how much is accurate to real data?
Yes, yes.
I showed in the figure, the first figure, I think, that showed the real data and our system solutions. But
Sir, it's a figure, but what is the order? Maybe it is
no,
up to
no, I haven't checked the. Okay, but in MATLAB, when we use that method to find the solutions, uh, I think we can say that if, for example, the error is more than one special special value, it stops. Is less than a special value, it stops.
okay, error
Yes.
tolerance is.
Yes.
Okay, if you increase the degree, can you increase the degree, sir, of that polynomial?
Maybe, yeah, maybe, but maybe the calculation time is more than, will be large, will be more, will be very, it will make many time to calculate, 2 time.
Okay. Okay, thank you, sir.
Thank you.
Sir, I created one doubts as Dr. Santosh asked you. Why you use here Newton? Why didn't use Lagrange one?
Uh, did, actually, there is different ways uh, to calculate numerical solutions. This was our first choice, and maybe we use some other methods in some other papers.
It is a choice or accuracy.
Um, we choice, it is our choice, just our voice
Your
choice. We
choice.
didn't compare this method with other methods yet. We
But
didn't.
But as far as I have done many articles in fractional with integer and stochastic one,
Okay.
I've done more than 15 articles
Mhm.
about Lagranges and Newtons. I find Newton is better than Lagrange, and we have the good accuracy for Newton rather than the Lagrange one.
Thank you very much. If we can have a common work and you do that part of the
Yeah,
paper
sure, sir.
to get the better results.
Okay.
Thank you very much.
Okay. Nice talk, sir.
Thank you.
Okay. So no more questions, I think. So thank you very much, Dr. Rumi.
Thank you very much. Thanks again for inviting me to be in this great event. Thank you.
Okay.
Thank you, sir. That was really informative. Now I request our session chair to felicitate sir with a token of appreciation. I request everyone to give him a big round of applause. Thank you, sir. Now we will take a short break for tea, which is being served outside the auditorium, and we will be back here and meet again for our next sessions. Thank you.
hello, 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 hello.
we are here again, back after the break, and without any further ado, let me introduce to you our next session chair who will be joining our previous special chair, Professor M. Mursaleen. So, our next session chair is none other than our chairperson and organizing secretary, Professor Hemanta Kumar Nashine. So, please welcome and joining our next session chairs.
Yeah, good morning, all. Welcome in the next session, this session where we are having the four invited speaker. I'm going to invite the Dr. Ijaruddin. Before inviting, I can give the small introduction. Dr. Ijaruddin is a assistant professor in Jamia Millia in the Department of Mathematics. He's completed his PhD from the Aligarh Muslim University. His research area is the related to the first part of the title, that is the nonlinear analysis, and basically he's working on the iteration scheme on the fixed point theorems and the application on that one. So his title of the talk is some recent fixed point iterations and their applications. Yeah. So please have a big applause. Once again. Okay. Camera mask.
Good morning, everyone. Good morning, everyone, and thank you very much. Special thanks to Organizing Secretary Professor Hemant Kumar Nashini and Dr. Hemanta for inviting me. And I want to say two things before I start my talk because this is the my first talk before my esteemed teacher, Professor Musaleen, and because I joined Aligarh Muslim University Aligarh as a UG student in 2003. So for 2 months, he taught me one course, and after that, he taught in MSc. So I'm feeling great honor. Okay, he is the chair. And also, when I joined my PhD in Aligarh Muslim University in 2011, so after that, I'm continuously learning Professor Ajay Kumar sir, and even after joining Jamia Millia Islamia, whenever I invited him for giving talk, so he always accepted and shown me a great affection, and always he is a benchmark for us and extremely extremely kind to me. So thanks to you people both. So I'm an assistant professor of mathematics at Jamia Millia Islamia, and I am going to share my recent finding with my students only. And I'm a learner, so I'm not the expert as Professor Nashini says. So I am the learner, and I'm going to show uh, some basic things about the theory. So this is the I will share with my experience from my guide. My guide is Professor Imdad, very senior professor. So which I learned some basic. What are the basic of the theory? And I will show some of the recent finding with my 3 PhD students who was already graduated. So as there are two talks has been made on fixed point theory, so I will skip the common part which already been discussed. So better next करना पड़ेगा. Okay, this was the outline of my talk, but because of we have been listening 3 talks, so I will start. Okay, आपको शायद रोकना पड़ेगा अपना हाथ. Okay, so usually we think that what is the fixed point theorems? So by means of the fixed point theorem, we mean a statement that we can have a guarantee of the existence of fixed points. So what we usually have in the fixed point, there are two things, either a underlying domain or we have a underlying mapping T. So we usually say that T is a map from X to X. So depending upon the situation where we are working, so this X has been decided. Sometimes it is a discrete set, sometimes is a uh, metric space, sometimes it is a Hilbert space, sometimes is a Banach space. So we only observe that there are two things, an underlying mapping T and an underlying space. So by means of fixed point theorem, we mean a group of statement. Either we are putting the condition on underlying mapping T, or we are putting the condition on underlying space X, or we are putting the condition on both. So with the union of these conditions, we are getting the guarantee of the existence of fixed point. So this is the meaning of the fixed point theorem. So due to three basic results, we can divide the fixed point theory in three broad categories. Number one, Tversky fixed point theorem in a very classical journal, Pacific Journal of Mathematics, and statement is very exciting. Every order preserving map. So here what we are doing, we are putting the condition on underlying mapping. Our mapping should be order preserving. Every order preserving map defined on a complete lattice. So what we are doing, we are putting the condition on underlying set. Our underlying set has to be the complete lattice, so it will have the fixed point. Another interesting and basic theorem is Brouwer fixed point theorem, and it falls in the category of a topological fixed point theory. So again, the statement is really appreciable here. Any continuous mapping. So what we are doing, we are putting the condition on underlying mapping. Any continuous mapping defined on closed unit ball of Rn. So what we are doing, we are putting the condition on underlying space. Closed unit ball of Rn has a fixed point. Okay, so it is worth mentioning here that if we suppose n equals to 1, so if n equals to 1, so we can observe that closed unit ball can become the interval here. So this is the one-dimensional version of Brouwer fixed point theorem. We can start that if f is a self-continuous map, then it has a fixed point. So it is an undergraduate material, and the plan of the proof is really simple. It is a consequence of intermediate value theorem. In most of the undergraduate course, after the some intermediate value theorem in real analysis, so we used to have that. But I want to say something about this very exciting theorem, Brouwer fixed point theorem. Proof on the real line or proof for n equals to 1 is very simple. It is an undergraduate material, but as we move or as we extend the degree of extension, or even the proof in R2 is very complicated, and it's involve many higher concepts of the mathematics, like algebraic algebraic topology, and some other higher concepts. So there are many versions of the proof, and this is such a basic theorem that there are many versions of proof, and people are looking simpler version of proof or elementary proof. So here there are two very recent. The theorem was proved in 1912, and the paper has been appeared in 2019 as well as 2022, and the title is An Elementary Proof of the Brouwer Fixed Point Theorem. So people are looking the different version of the proof. So there, because here many people are working in fixed point theory, so I want to give the suggestion that the people should at least see the one or two proof of this basic theorem. Because I was talking yesterday with some students of fixed point theory, and I asked, did you see any proof of Brouwer fixed point theorem? So their answer was not satisfactory. So it is a very basic theorem of the theory. So you people should see. So there are different versions of the proof, and a very exciting survey article by Shi Park. Shi Park is a very senior Korean scientist. He wrote 90 years of Brouwer fixed point theorem. And very recently, and I met Professor Sompong Thompongsa recently. He was saying that he is still working on elementary proof, and very in near future we will see one or more proof of this theorem. So I want to mention this one. about this very basic theorem. And this another very basic theorem, Banach contraction principle, and people used to say it is the metric fixed point theory, and or you can say that it is the most utilized part of the fixed point theory. And again, you can see the statement, any contraction mapping. So what we are doing, we are putting the condition on underlying mapping. Our underlying mapping has to be contraction. And the second condition, you can see that defined on a complete metric space. So what we are doing, we are putting the condition on underlying space. So in both way, what the guarantee is that you see that you will have a unique fixed point. In earlier fixed point theorem, in either Brouwer or Tversky fixed point theorem, you get the guarantee of existence of the fixed point. But in the Banach contraction principle, you not only the guarantee of the fixed point theorem, but you can also that you have the guarantee of the uniqueness also. So this is the great advantage of this one. And the idea of the proof is very simple. The idea of the proof is that if you select a point, arbitrary point of the domain, suppose x naught, if tx naught is x naught, so this is the fixed point. So there is nothing to prove. So suppose tx naught is not x naught. So suppose this is x1. So x1 is tx naught, x2 is tx1, x3 is tx2. So in such a way that you generate a sequence, and this sequence is called basically Picard iterative sequence. And by use of the contractive condition, you can show that this sequence is Cauchy. But as our underlying domain is complete, every Cauchy sequence is convergent. So this sequence will converge to a point x in x because of the completeness. So now our claim is that this limit is nothing but the fixed point. And again, by the use of the involving contraction condition, you can show that this is the unique. Now, as I mentioned earlier, that there are only two things involved, either an underlying domain or an underlying contractive condition. So the earlier research of the fixed point theory was confined to the extension of the Banach contraction principle via weakening the underlying contractive conditions on underlying mapping. So there are many contractive conditions. To mention a few, I listed some name. This is not the exhaustive list. There are many contractive conditions. Some are useful, some are routine generalization, some are even in later we can see that they are not the actual generalization but the particular cases. So there are many big lists. I wish to mention that one paper by Professor B.E. Rhodes. Professor B.E. Rhodes wrote a paper where he generated a very interesting machinery. I usually say machinery, where he constructed a function, and by giving that very much function, he can control a more than 32 contractive condition. He constructed a implicit function, and he proved a fixed point theorem, and by giving some particular cases. So this is a very exciting paper also. Okay, this is another direction. As I said earlier, another parameter is to change is the underlying metric structure. So underlying metric structure, there are many. You can see that partial metric topology or new approach to generalized metric spaces. So people are playing with the condition of the metric space. But in this direction, whenever someone is working in a generalized metric structure, so the people has to be very careful about the topology generated by the new generalized structure. So in this connection, recently with my guide, and he is my junior colleague, M. Asim, we introduce a new generalized structure. In this paper, we generalize previously existing seven metric condition. But the advantage of this paper is that in this paper we completely describe the nature of the topology generated by the newly generalized metric structure. we describe the topology, we describe the how we can overcome, because it is very well known fact that the topology generated by the metric, natural metric, is Hausdorff, but the topology generated by the generalized metric structure need not be Hausdorff. So when the topology is not the Hausdorff, so we can face the problem in get the uniqueness of the limit. So in this paper, we construct a new unifying approach of a metric, underlying metric, and we discuss entire and completely about the topology by the newly generalized structure. So this is an interesting paper, and but I will focus on this. So now we already seen that contraction. What is the difference of the contraction? Is that distance between the images must be less than the original distance by some. But if distance are same, so Banach contraction principle may not be true. So here you can observe that x equals to r, which is a, with respect to usual metric, it is a or the usual, it is a complete, and tx equals to x plus 3 is a translation map. It doesn't have fixed point. It is an example of a non-expansive mapping, which is not a contraction, but Banach contraction principle does not hold. So in this connection, I wish to say that Banach contraction principle was proved in 1922 after a long gap of 43 years. After a long gap of 43 years, these are the three basic, or one can say the basic fixed point theorem in the category of non-expansive mapping. And the statements are really exciting. So due to some unavoidable circumstances, because Banach contraction proof was in a setting of a metric space, but due to some additional advantage of a Banach space, the people has to confine their study when they were dealing about the non-expansive mapping to the Banach space. So this is the very famous Browder, Kirk, and these are the very basic paper. Those people are working in the fixed point theory. The people should see these two paper, and the statement you see that every time you see let K be a non-empty bounded closed convex subset of a uniformly convex Banach space. So, and in the Kirk theorem, you can see that a weakly compact convex subset of a Banach space with normal structure. Here, uniformly convex Banach space as well as the condition of the normal structure are geometrical properties that not only depending upon the choice of the space, but they are depending upon the choice of the norm also. So these are the very exciting geometrical properties. Another example, one can see that if x equals to minus 1 to 1, and if we take the example tx equals to 1 minus x, when x belongs to x, so here you can see that this is an example of a non-expansive mapping, which is not contraction again. Half is the fixed point, because t1 by 2 equals to 1 by 2. If you generate Picard iteration for suppose x equals to x not equals to 1 by 3, if you generate the Picard iteration, so Picard iteration does not converge to the fixed point. So you can see that in respect of the non-expansive mapping, Banach contraction principle does not hold in the second part also, because if your involving mapping is the contraction, your Picard iteration must converge to the fixed point. So this is another direction. You can observe that this is a non-expansive mapping. You have a fixed point, but associated Picard iteration does not converge. So now there is a need of device or construct iteration schemes. So now here we are confining our study either Hilbert space or Banach space. K has to be convex set, because this is the Mann iteration, this is the basic iteration process to approximate the fixed point of a non-expansive mapping. So here you can observe that because this is the convex combination, so that's why we are taking our underlying domain. K has to be convex. not only Hilbert space or Banach space, because we cannot take the metric space, because in metric space we don't have a linear structure. We cannot add two element, we cannot have a scalar multiplication. So even we cannot talk about this convex combination. So for studying man iteration or iteration schemes, we have to confine our study to either Hilbert space setting or the Banach space setting. So man iteration, and you can see the next one is Ishikawa iteration. You can say this is two-step. This is the two-step Ishikawa iteration, but the motivation was a little bit different. Ishikawa utilized a bigger class of a mapping, but you can observe that pseudo contractive mapping, compact mapping in a Hilbert space. Sorry, this should not be there. It should be pseudo contractive mapping, which is the bigger class. But again, Man study their result in the class of a uniformly convex Banach space, but Ishikawa has to restricted himself only up to the Hilbert space setting. So again, you can observe that they are indeed need the convex combination. They are indeed need of scalar multiplication. So these are the two basic iteration process. So after that, there are many iteration process with a different motivation. Some people introduce, for example, if you see here, Noor introduced a new approximation scheme, but they utilize their iteration scheme to prove the variation inequalities problem, to get the solution of variation inequalities problem. Professor Agarwal, Rogan, and D.R. Sahu, they constructed many iteration scheme. So here people are constructing iteration scheme with their motivation, with their need. So here you can observe that. So in this connection, this was the my first PhD student, Chanchal Gorodia. So in this paper, we construct a new iteration scheme involving two mappings. Why we are taking two mapping? Because common fixed point approach has a very exciting application in minimization problem, or you can say the composite minimization problem. So suppose if you are solving the minimizer of a fx plus gx, such that a point which is the fixed point of f and a point which is the zero of x, if they are the common, so this problem can be used for the minimizer. So here in with this paper, we did with my PhD student, and after that, there are three papers. So this is another paper in with my student Chanchal again, new iterative scheme. So here we construct a new iterative scheme for solving split feasibility problem. Again, we construct a new iteration scheme for solving delay differential equation. And the interesting part of that, most of the time, our underlying domain is uniformly convex Banach space. So yesterday I listened one presentation on a application path. So I wish to mention that the whenever you are applying uniformly convex Banach space, so you must concern about the example, because CAB with respect to supremum norm is not the uniformly convex Banach space. In some presentation, I observed that the student constructed a map whose domain is a C01 with respect to supremum norm, and they utilize a theorem whose domain is uniformly convex Banach space. So they have to be very careful about. I pointed some of the students. So because whenever you are going to apply one result, kindly check every condition. So I saw two papers, so I pointed them. So in my paper also, I constructed one theorem in the setting of a uniformly convex Banach space, and I put some more condition on underlying domain. Then I able to remove the condition on uniformly convex Banach space. So this is the concern to say something. And these are the two more paper. Uh, so this is another paper with my colleague Javed Ali and Fahim Ali, and also these are the two paper with my PhD student Sabia Khatun. where I have done modified proximal pine algorithm. What is proximal pine algorithm? Uh, suppose f is a function. Suppose f is a function. We want to find out the minimizer of this. We want to find out the minimizer of this, and a is another operator, such that the zero of that operator is nothing but the minimizer of this function. So involving these two, one function, one another function. If we construct another function, and we usually call that function as a resolvent, that function is a resolvent such that the fixed point of the resolvent is nothing but the minimizer of the function and the zero of operator. So this problem is called as a proximal pine algorithm, and initially it was given by a very famous mathematician, Rockefeller. He claimed that on the Hilbert space, resolvent found to be naturally non-expansive mapping. Naturally, if A is a maximally monotone operator and f is a lower semi-continuous function, and A is a maximally monotone operator, then the resolvent was found to be non-expansive mapping. And he proved that if we are imposing the condition of the asymptotical irregularity, so the resolvent is converging to the fixed point. And that paper was appeared in the Siam Journal Optimization. And after that, people are looking at different iterative combinations and putting the condition of the resolvent, and they are getting. So in this paper, we have modified proximal point algorithm. And these are the two papers. In this paper, we study for the one map, and in this paper, we construct a modified proximal point algorithm involving finite many family of asymptotically non-expansive mapping. So both in the same year. And also, these are the two papers. In one, we construct a new iteration scheme for solving boundary value problem, and here we constructing for fractional differential equation. So these are the. But more interesting, this is the jump. This is the one jump. We know that the Banach contraction principle says that T is contraction. What is the meaning of the contraction? If d of tx comma ty is less than k times dxy for all x comma y in x. What the Renner-Roering did, he took x comma db complete matrix space, endowed with a partial ordering, and we can see that later on what is the compatibility of this ordering and the matrix structure. And he says that, Renner-Roering said that, they say that d of tx comma ty is k times dxy for all those xy which are comparable. So with the initial, if there is an initial point which is comparable with its image, then it has a fixed point. So Renner-Roering, and almost in the same year, in the proceeding, and almost same year, Newton and Lopez. But the motivation was different. Renner-Roering applied their fixed point theorem for solving matrix equation, while Newton and Lopez applied their findings to solve the periodic boundary value problem. They solved the periodic boundary value problem with these mapping. So the people were, because the now metric structure has been set up with the compatible with the ordering. So now the people are looking the proof of the great Browder and Kirk theorem. They are compatible. So they have proved there are two men. One is Bashar and Khamsi and Abdul Latif and Songol. So they prove some very exciting existence theorem involving for monotone non-expansive mapping. So they have done. So after that, we decided to study some iteration. This one. So these are the iteration process. We study iteration process for monotone non-expansive mapping. So most of the time, our domain is order Banach space. So here what we have to do, every time we have to be very careful about the geometric conditions and their order theoretic version. For example, we have OPL condition. So what is the order theoretic version of OPL condition? If we have a normal structure, so we have to be very careful about the order theoretic version of normal structure. So with the help of my students, we produce these 4 papers, and every time we involve Mann iteration for monotone non-expansive mapping. Here we Fibonacci Mann iteration for monotone non-expansive mapping, and this is one of the most exciting paper of my life, because it's our one of the most strongest journal, with originally with Newton. We constructed in this paper a fixed point theorem for monotone nearly asymptotically non-expansive mapping in order Banach space. So this is the some contribution in this direction. Now again, we see that Newton and Roering did X is a metric space together with the ordering. So there is a famous mathematician, Polish fixed point theory. What he did, X is a metric space together with the graph structure, and he proved contraction theorem for, you can say, the G contraction, and he cared about the contraction condition only for those points which involve or which found to be in the edges. So after that, these are the four papers where we study iteration process involving graphical version of contractive conditions or non-expansive mappings. So these are the now very recently, or not very recently now, the 8 years before, what these two guys, one is my guide and one my junior. Now you can see that X is a metric space in Banach contraction principle. X, D together with the ordering, partial ordering in the Renner ordering and Newton paper. In Jeshmeshki, X, comma D is a metric space involving with the graph. Now this graph has been replaced by an arbitrary relation, and this paper was after in 2015 it has been received attention of the people, and more than 190 citation has been received for this paper, and people are working this. And very recently with my student, we have two very natural contraction. One is called the Grati contraction, and one is also this weak almost contraction. So we produce relation theoretic fixed point, and in this paper we have a very interesting application to LCR circuit. So now what is the future interest of us? So we can see the relational. So we want to study the Kirk fixed point theorem, which is the basic fixed point theorem, in the setting of Banach space involving with arbitrary relation. We want to look for that. And also this is the one very interesting domain, that these 4 or 5 people, Suzuki, Garcia, and Garcia also, they have introduced a very classical extension of generalized non-expansive mapping. So we can study not only the existence, but we can study because this Tomonari Suzuki, a student of Takahashi, and also these two guys, Omoya and Kosaka, they have their alpha should be there. So they have introduced, and also one Garcia, this is a Spanish guy, and this again Lohner in orbitally non-expansive mapping in bullet. These are the very classical generalization depending upon the situation, because if you see that the projection operator need not be non-expansive in the setting of a Banach space. So fortunately enough, they found to be alpha non-expansive mapping. So this was the motivation of introducing this generalized class of a mapping, and every time they utilize the geometry of Banach space. So this is the another point. So we can study the iteration process involving these maps, different iteration, different mapping. So the life is on. Very few iteration can be studied with respect to especially this class of the mapping. There are many papers appeared after Suzuki, also the Garcia. People name the condition C lambda and N mu, but this is very unexplored. I saw only one paper about this very exciting class and very basic paper, orbitally non-expansive mapping. Here they utilize. So this is very exciting. And also, last 2 years, this is another very interesting open challenging problem. Does the Kirk theorem hold good for multi-valued non-expansive mapping? The theorem is very old. The contraction version was proved by the Nadler in the Pacific Journal of Optimization, and some partial answer some partial answer was given by these exciting mathematicians, and every time they utilize some geometric condition. So Lamy do utilize the OPL condition. What is the OPL condition? Suppose xn is a sequence which is converging to x.
Hello, Dr. Izar.
Yeah.
You have 5 minutes more.
Okay, sorry, this is the last slide.
Thank you.
Okay, and they use OPL conditions, and TC lim utilize the again uniformly normal structure, and Edelstein utilize the asymptotic center. So these, and recently three pupils, Kirk and Massa, constructed asymptotical and Shibeshi center. They remove some, they took the weaker version of the uniform convexity, and Thomas Damagunzo Benavides, Spanish man, they introduced a one property people used to call DL property, and they prove some existence theorem. But these all are again Sompong Dompongsa, his students at Tapolco Oaxaca, they utilize DL condition introduced by them, and also Sompong Dompongsa with Thomas and Encheli, they use Jordan von Neumann constants. So is still their life is on, because there are many geometric condition on Banach space, Maluta constant, weak. There are another weaker form of the OPL property, and also the weaker form, the normal structure, which can be utilized. So I'm studying with one of my students this direction, but still I could not find any generalization or any fruitful findings, because it's require a lot of efforts with respect to geometric condition involving Banach space. So these are my future direction. So thank you for kind attention.
Yeah, thank you. Now the floor is open for the question answer session. Very good presentation. Just I have very small question. You have presented a lot of thing here. I not understand much. What is your final conclusion in this talk?
Okay, my talk is basically we start a journey of a Banach contraction principle, and then we move towards the Ranner rating and Newton findings with order structure. Then we move Jashmeshki, where Jashmeshki replaced the order partial ordering with graph structure, and Alam at Imdad replace this graph structure with arbitrary relation, and in between them there are existing contraction condition and existing iteration process. So involving Renner Rering introduced monotone version of Banach contraction principle. We study some existing contraction with monotone version, and we also study some iteration with monotone non-expansive. The graph structure, then some existing contraction, some existing iteration. We study graph structure involving graph non-expansive mapping, then relation theoretic version. Banach contraction proof was by Imdad, and we prove Grathi contraction as well as almost nonlinear contraction, and we will try to employ now relational non-expansive mapping for monetization for non-expansive map.
I have seen in your talk from beginning to last any result like this. What you are saying?
Yeah, because in
To
the
understand me or other audience.
last 3-4 talks, people have been repeated those results, so that's why I omitted those.
No, results not repeated. What you are saying, nobody has told this thing.
Okay,
Okay.
okay,
Basic, everyone told about fixed point is fixed.
okay.
But what you presented here, what you are saying, where I have not found here. And how a student will understand. This is the main thing.
Okay,
Okay,
so
thank you very much.
okay, so you are saying that I should write results also.
Dr. Izar, wonderful survey of the fixed point theorems. I would like to know that are we exploiting the uniform structure of the metric spaces?
Sir, here uniformly structure very partially defined for metric space. It
Yeah.
is defined for the Banach space itself.
Yeah, are we exploiting the uniform structure? If we are exploiting the uniform structure, then I believe there are many more uniform spaces,
Yes, sir.
like topological group is a uniform space. So why people should not try over getting to such structures?
Sir, basic here uniformly structured means close bonded convex subset of a Banach space have a non-diametral point. Here, this is the meaning of a normal structure. It was introduced by the Brodsky and Milliman. If C is a closed bounded convex subset of a Banach space such that it has more than 2 points, so it must contain a non-diametral point, then we will say our Banach space satisfied normal structure. This is the meaning of normal structure here.
No, I'm not talking about normal structure. Uniform spaces are, you understand,
Okay.
topological
Ji.
space, uniform space.
There is a one professor who did something about Hashim bin Makhail, who
Hashim.
proved Brouwer fixed point theorem. He
Mm.
proved some exciting theorems on, but very few on uniform spaces.
Okay.
Hisham.
Okay, so why not people try for topological group? Uniform space is too general.
So,
Why not to try for topological groups?
sir, they have proved some theorem especially in locally convex topological spaces also.
Okay.
Keketan and Kaifan has proved many fixed point theorem. Even
Okay.
Kaifan has proved for topological vector spaces, and this theorem was utilized by Professor J.F. Nash to prove the share market problem and earn the Nobel Prize for that.
Okay.
That particular fixed point theorem by Kaifan.
Okay, thank you.
Good morning, sir. Very nice presentation by you. But I am not able to get many more things because I am not belong to this research area. Still, sir, one doubt that in your theoretical work, how could you say that your answer is correct? Whatever you are finding in your result, that means how you are checking your validation. Yes, sir. So, from the proof,
Or you can say that there is no data involved in our study.
yes, yes,
No data is involved.
no data is involved. Okay. Simulation is not there. Okay.
So, good morning, sir. A nice talk of you. Sir, I studied many papers of you and many others also in this fixed point generalizations of non-expansive mappings and iterations, many. But the results almost are same in all papers. While you are just generalizing the non-expansive mappings, iteration techniques in CAT0, Banach space, either in hyperbolic metric space, but almost all the results are same. So just my one question is there. So if every results are the same, just a geometric property is little bit different for CAT0, Banach, and hyperbolic metric spaces, it's okay. But one thing is there in our papers in fixed point theorem approximations, there is one thing that's a necessary and sufficient condition that is called approximate fixed point property, norm of txn minus xn equal to 0. Why we don't people are working on that to remove that condition and introduce a new one? Can we do it?
If you see the paper of Afkar Azam, they have in Bulletin of Iranian Mathematical Society, they have a different route. For example, we have to go out from, we are many people and we want to go out from this room. So either one, either this. So
But
Apkar Hazam has removed that condition.
approximate fixed point
Yes,
property.
yeah, they have done, but they have to restrict it themselves. Apkar Azam and Ismaili, and but they have to restrict it themselves for. They have to put the condition on parameters. They are not natural. For example, we want to go out, so this is the one way we can break this wall, and we can go out. We can go out.
Mhm.
So those condition was so much complicated, but they have break that condition.
But sir, will you believe that that condition approximate fixed point property txn minus xn equals to 0, that is the strongest property of the paper to find out the approximation of fixed point using iteration
There
techniques?
is no actually there is no other way. For example, only these two gates or these gates. So this is not the not the strongest, but you can say the hardest.
Yeah.
But in only two more condition I could found in the literature so that we can avoid this. One paper was Afkar and Azam, and one paper by the student of Takahashi. You can see the Kimura
okay,
and Kosaka. Kimura and
yes,
Kosaka.
yes. They
So-
introduces a generalized non-expensive mapping.
No,
Alpha
like
non-expensive.
non-expensive, Omoya or Kosaka, they are the different one.
And sir, last question, mine. Sir, when we are going to stop to make a new iteration techniques time by time, every time that iteration techniques are following by the same one, just generalize little bit changes in the x and y and t and something. But what is the benefit of that to making a new iteration that is almost doing the same previous one?
So you have a different motive. For example, we are getting PhD. Some people are getting PhD for academic work. Some people are getting for in CS and other background for getting promotions. So iteration process, everyone has a their own. Sometimes the people look for the complexity because if you see that there are some iteration which claim that less number of
Time.
iteration,
Yeah.
but their computation time is higher than the simpler even than man.
Yes.
But their number of iteration has less, so their motivation, because for example if you want to go from Bhopal to Delhi, we have lots of money, take the ticket. If we have a less money, we will say by train. So some people, and most of the thing, because for example I mentioned here Renoring and Newton, they have produced same kind of monotone version of contraction principle. What different motivation? One applied their result for matrix equations, and one applied there for periodic boundary value problem. Almost same results, but their motivation was different.
So actually we are initial researchers.
You should see why you are going to where you are going to apply your iteration process.
Okay.
This is important thing.
Yes, yes.
Another problem is that if you are going to apply your result for solving differential equation, so always there will be a question for the uniqueness.
Uniqueness.
So
yeah.
people will ask
Yes.
why you are working on the ill-posed problem. So you must be prepared for that also.
Okay, sir.
Okay, why if there are two iteration process, you are comparing,
Yes.
but their fixed point are different because their fixed point are not unique.
Yes, yes.
Tx equals to x square, these have a two fixed point,
Okay.
and you can get a kernel which can satisfy this assumption also.
Yes.
So with the help of that kernel, you will lead towards two solution. So you cannot compare in that situation.
Yes.
So
With
you have to be
example.
very careful.
Yes.
If you are going to apply your iteration process to optimization problem, so always you have to be restricted yourself for either uniformly Banach space or the Hilbert space. So now you cannot apply OPL, you cannot avoid OPL condition. Sometimes you have to impose the condition of uniform smoothness also.
Sir, instead of OPL property, we can use Freshet differential norm
Yeah,
also
that's
because it
also-
fail for the uniform.
Yeah, that's why I'm calling smooth, uniformly smooth.
Okay, sir.
Banach
Okay.
space.
Thank you, sir. Thank you. Thank you so much, sir.
Also, you can see the Gaussian differentiability also.
Okay,
But
okay, sir. Thank you.
every time you have to look for that which situation you want to be.
Thank you so much, sir. Thank you so much.
Thank you very much, Dr. George.
Thank you very much for your nice talk. It was very informative. It was just a survey talk, I think. And so we are very much thankful to you for your nice talk. Thank you once again.
Now I would like to ask our session chairs to felicitate, sir.
That's a
Can we have a big round of applause for Sir? Let's search start session.
Such.
the next. So now we are having the next speaker, Professor M. Sajid. So before inviting, so I'm having the brief introduction of the Professor Sajid. He's currently Professor of Mathematics in the Department of Mechanical Engineering, College of Engineering, Qasim University, Saudi Arabia. He obtained the PhD in mathematics from the Department of Mathematics and Statistics, IIT Kanpur. He was the post fellow under the NBHM scheme. His main research area is dynamical system associated with the fractal, chaos, bifurcation, fixed point theory, iteration process, and the complex analysis. Now he is going to give a talk on the topic computational techniques of fractals and chaos in nonlinear dynamical system. Over to you, sir. Thank you.
Hello. First, thanks to organizing committee and organizer and convener of this conference. They have given chance to me to present something here on something new in associated to this conference, nonlinear system, fixed point theory, etc. So today my talk is based on computational techniques to compute fractal and chaos in nonlinear system. So here nonlinear system we take as a dynamical system because most of theories around us, whenever we try iteration, recursive process like that. So we connect our talk this nonlinear dynamical system especially. So so sorry. Okay, good. So now we start my talk with I think yes, okay. This okay. Okay, good now. So now we start with my talk with this abstract. I think you have most of them have they seen this abstract. So my main purpose of this talk to present something on some techniques of fractals and chaos in dynamical system. Especially we have taken dynamical system as a nonlinear dynamical system. Recently it is seen that many disciplines of science and engineering are concerned with nonlinear dynamical system, and moreover fractal and chaos are more advanced technique for visualizing analyzing complex problems. And most of time what happened whenever we have scientific process, we model our things in a mathematical form and mathematical expression, and mostly mathematical expression will go in the equations and equation or formulas, and then we can convert these formulas in algebraic equation, simple equation, or maybe difference equation, maybe differential equation, a lot of type of differential equations. So in these equations, many equations are linear and non-linear. Here I will present our main focus is nonlinear dynamical system. But before nonlinear dynamical system, I give you something linear system also. And next is, in finally, we will show that why we something say fractal and why we say something is chaotic behavior. I will show by mathematical theory or computational things here. So we go in this direction. So we start with this simple pictures. So these pictures, first picture is simple is generate. We can generate through simple a differential equation system. Second is just picture a photo, and we can looks like a photo, but sometime we can generate this picture through equation that is called fractal. I will show how to generate. Third one also a fractal. Fourth one also a solution of differential equation. So how to go through mathematical equation on these type of pictures. So step by step I go now. So long time before, Gauss said mathematics is queen of sciences. So something is like queen is like a something. Whenever queen come in our mind, what we say, we think about very beautiful, very handsome, or something like that. So I will show you today mathematics also beautiful like a queen through beautiful things, not by formula. It is by looking. When you look and yourself, you can say, yes, this is a beautiful things inside the mathematics. So I will tell you about this also. And next is we have now these things. What are the shapes of trees, mountain, and clouds? We have a lot of names around us, but is there any specific name for in mathematical form? And we can say more about it. Does lighting travel in a straight line? Why two pieces of cup? If broken, then again we join. They will not fit together. There is some crack. And how big they are and how long they last. These are a lot of questions we have now. So we go step by step now, and we can see that here. One more thing here, Galileo told in 1614, universe is written in language of mathematics. After looking today beautiful pictures, you can say it is more very accurate sentence about language is written in this universe is written in terms of mathematics. Without mathematics, we cannot describe the nature. So mathematician Benoit Mandelbrot was first recognized the obvious problems. Clouds are not spheres. Mountains are not cones, coastline are not circle, bark is not smooth, nor does lighting travel in a straight line. Why he told about this? He told because before that fractal theory, we use mostly Euclidean space to approximate our things or maybe some special type of spaces. But after introduction of fractals, now we have new theory and we can describe natural object in simple way in very less computation or we have very less error in the system. So now what are the fractals? First thing is this, what are the fractals? This is the thing. So no hard and fast definition of a fractal. Fractal can be defined in terms of characterization of things. Till now there is no fixed definition of a fractal. So it may be irregular shape and it may be self-similarity or fine structure or house of dimension is strictly greater than its topological. Some of characteristic are here. Maybe more characteristic you can find in the literature and you can describe the fractals. So what is meaning of this? So you can understand by some more pictures. Today now you see this. In this picture, you can say similarity. If you have similar object, you get just cut and cut and cut. You get similar objects. So this is the one kind of fractal. Another kind of fractal we have that is a fine structure. So in that case, we have like this. We go inside and inside and inside and inside. We have a special kind of picture inside and inside. You get similar kind of structure again. We can describe this as a fractal. We have another kind of fractal like this. We can say if something zoom out, zoom out, zoom out, you get similar type of structure. So today we describe this picture through fixed point theory, and why we apply the fixed point theory, I will explain. Some picture we can generate by linear system. Once some of picture we can generate by non-linear system. So linear and non-linear, which is important, we cannot say. It is just this, which is important for me. How can define our structure? That is the important. Linear and non-linearity is not the issue. I will show you. If we construct a bicycle, we need a simple material. We can construct a bicycle. If we want to construct a helicopter or aeroplane, we don't use material of cycle. We use a special kind of material. Also, same way, if we have built a cycle, we don't use a material of a aeroplane because that is very costly. So depends on our requirement. According to that, we use the formula, we use the technique, we use the convergence. Somebody asked the question about fixed, why don't change NT this? It depends on convergence, how to reduce your total computation, how you do your work fast, either by hand or by computer. So according to this, you go on the convergence, you define your parameter, you define your iteration, you define your bound. If our work is not finished within a time, within a domain, within a whatever you specified, so it is not useful for me. So so there are many things like that. Okay, so go to next now. So go to next. First fractal, we can construct a Cantor set like this. In the Cantor set, we take a line, we cut 1/3 part. Again, we in each small segment, we will cut 1/3 and continue this process. We get a fractal. I will show also mathematical construction of some of the fractal, and some functions are linear, some functions are non-linear. Some linear function give you a very complicated structure, and sometimes non-linear function will not give you result, but sometimes linear give you a result. Sometimes linear will not give you a result, sometimes non-linear dynamical system give you the result. Okay, so more interesting is this fractal. If you have a line, you can understand more about how to construct a fractal. Just you take a 1/3 line cut and put two small lines here, and continue this process on each small segment, and this. So here is just geometrical construction, you use the scale. Here is no mathematics, but I will show also mathematics, how to do through mathematics and what we need in mathematics. That is very important. To need is this, we need iteration, we need convergence is very important. If no convergence, no fixed point iteration theory, then we cannot construct these type of fractals. Okay, we can construct fractal without convergence also, maybe not diverge system. That is different. Fractal does not only depends on converge. Fractal is a just image, you generate image by any technique. But most of time we construct fractal through convergence because we have a basin of attraction. We construct the stability, we find a attracting point find, and we find that how many points will converge. We plot that, just it is easy to do. So every time people do this, so we ever feel that fractal will come just by basin of attraction. No, it come by any other way also. So we have another kind of fractal. If we take a triangle and we cut 1/4 in the middle and continue this process on small and continue this, and you get a fractal. So we have already shown how does it work, this fractal. Go to next one. We go to next one like this, Remke carpet. In this, we have a square, cut 1/9 part like this and continue this process. So we get a another kind of structure and continue this process. We get now this. So Sierpinski has given the name based on its design, because this design looks like a carpet. So they have generated different kind of cutting, and they have designed like this. So they say that yes, this is a like a carpet. So they have given the name of this fractal is carpet. Okay. So same way we can construct many more fractals. So in other kind of fractals, we can find also. So we have sometimes 3 dimension. So we can find also fractal in simple way. in 3 dimension, just cut in the middle part and again middle part, again we get a fractal like this complex structure. So we can also now we can construct many more fractals through iterated function system. So in this case, we use the construction mapping. Okay, fixed point theorem is around the construction mapping. We take a set of function. This is, I don't want to go to in more detail about this mathematics, but we use this mathematics in this, and then we define the how we can construct mathematically Cantor set. So it is like this. If we have a just Cantor set 0 to 1, apply 2 mapping, and we get on interval 0, 1, we get a next interval 0, 1 over 3, 2 over 3, 1. We get 2 segment. In these 2 segment, we apply again 2 mapping, we get 4 interval. So we get 4 interval. Like this, continue this process, and finally we can show the convergence because this takes many slides. So I have skipped all of the slide. I will show this through by 2 dimension. That is more interesting. This is not very much interesting because everyone know about Cantor set, how to construct in school in the undergraduate level. Those who done BSc or something topology. This is construction given in a topology. Okay, all topology books, matrix theory, this type of construction about Cantor set. First, every time first example is this Cantor set. So they have idea about this, but I say this idea you can use in a fractal. Now we construct a another things. So we use the 3 mapping, F1, F2, F3, and then we apply on the triangle. If we take a triangle, and on this triangle we apply 3 mapping, we get 3 small sets. So if you get 3 small sets, so continue this process, you get small, and then finally we can show the convergence here. F and X converge to so it is long theory behind this. This proof may be available 3-4 pages. If you find you are interested to find the proof, you can say the fractals everywhere by Michael Bachelet. So very good proof is given. Okay. So you can see there. So another thing is this, we can sometime our system is very complex. We cannot directly do through Cartesian system. We can convert in a polar form, and then you can again construct the fractal. So you can see like this. Another example like this, we take a 4 maps, but interesting thing this, these are our linear map, and we have very complex and very complicated and very interesting picture. Okay, so this is just we have generated through a 4 linear mapping, and we apply on this, and step by step it will converge to fern. So it is not a picture photo, it is a generated through a mathematical formula, only simple 3-4 linear equations. Okay, so we have very good theory. We can construct a fractal. It is a linear system. After this, we discuss about non-linear system because this conference and my talk focus on non-linear system. So linear system as well is important, but it depends on our need. What is our need? According to that, we apply the system. Today, our discussion about non-linear system in this conference, we discuss non-linear. In other place, maybe linear system, we will study. Just like this, if we want to build a car, we discuss about the car. We don't discuss about the aeroplane. If we have discussion about aeroplane, so we don't discuss about the bicycle. If we cannot put tire of the bicycle in the aeroplane. Okay, aeroplane tire you can put in the bicycle, but why unnecessary you make a costly bicycle? Okay, but bicycle tire you cannot put in an aeroplane. One side is work. Okay, so converse not true. Okay, so we go to next part, chaotic system. I say chaos in a system. So chaos is this like that around us, or you see the research paper, and inside the research paper we see that market prices are chaotic, not fixed. Traffic situation is chaotic, weather is chaotic, behavior of human is very chaotic, structure of brain is chaotic, chemical reaction are chaotic, explosion of volcano seems chaotic, So like that, a lot of problems we have. There is chaotic situation nowadays we are using either in newspaper or research paper or some other places. We say we have very chaotic situation. So it is like that. So chaos exists everywhere in the world. Okay, so we can see this situation in our around us. We can say yes, we are daily associated with these type of problems. We are facing traffic situation, we are facing market prices, we are facing traffic situation. So a lot of things we are daily facing. So we have chaos around us. So we are some of them daily face all problems, some of them maybe one or two problems, but we have a chaotic situation. Okay, so it's non-linear world. So because I told that non-linear system gives you a chaos. So first we go to chaos, we have to go back and see that around us things are non-linear or linear. So I say linear is not, we say not important, linear is also important, but if linear system will not work, then we have to go for chaotic system. For the chaotic system, we must know where is the non-linearity. So we must understand first non-linearity, then we go for chaos. If there is no non-linearity, don't need to go for chaos. Okay. So real problems and issue on the frontier of modern scientific, technological, economics and social researches are non-linear in nature. In Laplace world, everything was predetermined, no chance, no choice, and no uncertainty. So Laplace told no chance. So, but most of the system, most of scientific system, most of our system based on probability, random process. Okay, we are doing approximate more work, approximate work. But Gauss, these say so. Chaos theories say that you can do exactly, don't need no chance and don't think. So how to define the chaos, that is given now here. So we will see that thing here. What is the chaos? So chaos is this extremely disorder, irregularity and confusion. This is a simple meaning we want. We don't need mathematics, don't need scientific things. This is simple thing is extreme disorder, irregularity and confusion where is exist, then we have a chaotic situation. I already told about this, weather and traffic situation or like that. Now, what is mathematically, how to convert this problem in mathematics form? So we can convert this in mathematics form if we know the something like this. Chaos is phenomena that has a deterministic underlying rules behind irregular appearance. So if we have this phenomena in a system, then we can define mathematically chaos and determine the chaotic situation. We can quantify the chaotic situation. Chaos is not like if things we can just use. It is a situation. This is a behavior situation. Once we have to understand situation, then we can determine the chaotic situation. It is not like a fractal. When you generate some picture, you have a fractal in front of you. You can see many things inside the fractal. But when you have a chaotic situation, first you have to recognize it yourself. It is a situation. It is not an object you can just bring and use. Okay. So now go to how to understand what is the chaotic situation. So something is phenomena irregular, appearance irregular, underlying rules irregular, so deterministic. It is simple. Something is statical, something regular, but it is based on probability. We don't get 100% answer, but we get answer. Maybe 90%, 80%, 99%, but not 100%. 100% means done, no need probability. Okay. Random process is irregular but also based on probability. But last thing is this chaos. Chaos is irregular and deterministic. So this is the advantage. People have defined the chaos. Based on this, we can say that it has more advantage than other systems. This is our work, how to recognize the chaos situation, it is chaotic or not. So we have a tools for that. Use those tools in mathematically and apply, and you can find the quantify the chaos. Okay. So there is no standard definition of chaos. Chaos can be feature of the chaos are we have now like this. So in the feature, first is non-deterministic, non-linear. Then we have irregular, and last one sensitive to initial condition. This last one is very important and new things inside the definition. Initial to sensitive condition is something is sensitive, then we can determine the cures easily. Okay. So questions, there are many questions behind this. So what kind of nonlinear system exhibit chaos? And how does the behavior of nonlinear system change if parameter describing the system change? How do we decide if system is strictly chaotic, and how do we describe chaos quantitatively? What are the universal features found in many nonlinear systems? Are these features truly universal, or are these are different kind of chaos? And how does we understand this universality? And why what does the study of chaos scientifically, technically we have now? What are the philosophical and methodological implication of chaos? There are a lot of questions you have in your mind. So some of them I will give you answer step by step like this. So first we can see chaos in very simple system. Very simple system. It is a just second order second degree equation polynomial, very simple. You have rx1 minus a, it means rx minus rx square. Very simple system, but it is has very rich dynamical system. Many books are written on this, only this equation, to find the chaotic situation and describe the fractal nature of this system. So here we are doing, so till now we are, every time we say fixed point, and fixed point not conjoined, and then what is behind? So we have one more question about what is the behind. So I have answer is this: behind that there is not necessary always fixed point. You go for periodic point. You go for periodic point or cyclic system. There may be your period may be 2, 3, 4, 5, 6. Not necessary you stop your simple system. Just say fixed point, converge and stop. Because why we do mostly? Because we give example of linear system. Mostly we give example whenever asked to student what you present, they say we have given this example. In this example is that a simple a not linear system. So due to this case, most of time they have just one fixed point, try to one fixed point and converge immediately or not converge. They don't go for higher order system, complex system. There has non-linearity and you have many points. Not fixed point, you have periodic points. Or maybe other reason they use the only simple equation. And when you have non-linear system, you have a periodic point, then your dynamical system or your converge will become very complicated and not easy to determine. Due to this reason, everyone cut part and say it is example and this is a just simple linear system. Don't go far, because when you prove a convergence for non-linear system, your equation will become very long. Even simple, you see the proof of the convergence of a Newton method. Many pages you have to prove, show that is convergence more than 1 point something like that. So convergence, when you take a new kind of example, showing the convergence is very, very difficult work. So due to this reason, people cut the example and say this is system and converge and thus finish their work. Okay. So I show you how to convergence is there. In this case, simple example, very small equation, rx minus rx square. Very, very simple, no many terms, nothing is here. Then this has a very complex and complicated dynamics. So you see that here, in this case, when your point is near, r is near to 1, you have only fixed point. And after this, when you go long time, you see periodicity start, and near to 4, there is a very dark region, that is a chaotic situation. Before that, you have periodic point of period 2, 3, 4, 5, 6. So whenever we study the fixed point theory, we say give the example either here or in the review. I review the paper. Mostly people get one degree equation fixed or second, not go for higher dimension because system will become complex. They don't try. Okay. So go to next now. So in this case, okay. So I take a different kind of function, lambda x over exponential x plus 1 to power n. I use this for n equal to 3. We have found this type of bifurcation graph. So this is very complicated dynamical system. I have found a fixed point up to 16. So it took more time on computer, also simulation or by hand to calculate the fixed point. We get periodic point here, and we can show periodic point like this here. So this is a fractal, and here is chaotic situation. Dark region means. So first fractal is generated by this Mandelbrot. Yes.
Sir, try to sum up.
Time finish.
Yeah,
Very
try
fast.
to sum up in 2 minutes because we have two speakers are there.
Okay, that is okay, but little bit. Okay, I go fast now. Okay. So this is first fractal generated by some of them. So after this is for very simple equation. Z square plus C, very simple equation, but we have this type of good fractal. And now we go to fixed points. Fixed point defined, everyone know about this fixed point, so don't go to in detail. This is attractive fixed point, periodic point. In the Newton method, you can find the fixed points for simple function ZQ minus 1, and then you calculate the basin of attraction like this. We have 3 fixed point, we get 3 basins here for each fixed point, and we get like this. So we get this type of fractal. Convergence is very important here. Now go to another kind of fractal. We take this function associated to differential equation, and we find the fractals through, that is called Julia set, which is complement of basin of attraction. And now we have fractal like this for different of parameters. Here is fractal and chaotic situation both. Now we can construct this fractal like this. This is for a special kind of method, and they have this type of fractal. When you zoom it, the red region, you get this. And here is a small point, and each one you zoom it, you get this type of, for each small point, we have each small fractal, this new fractal. Again, you can zoom out, you have very good and very strong structure inside this. And we have another kind of fractal like this. This is another kind of generalized Aitken type methods, and we have these type of fractals. All are these dynamical system. We find the convergence and basin of attraction. We published this paper with Professor Anita Toma. This is dynamical system in complex plane. We have these type of fractals. So I don't go for more detail. Just another kind of paper we have is associated to polynomial degree n, and we have these type of fractals. And now we have these type of other kind of fractal for different kind of family of functions. And we have another kind of function when associated is exponential family. And we have new paper, this another kind, this is associated to sine function. We have these type of fractals. And these are comparison of two kinds of families, convergence rate. We have found the fractals. So fractal can be found in differential equation, and Lorentz find this in 1963, chaotic situation. This is dynamical system, Lorentz-like system, and we have these type of cycles, and we have system of 3 difference equation. And with this system give you this like a seashell. It is a fractal. We can generate through some choosing spatial parameters. Now we have another kind differential equation system. We can generate the fractal and cycles. We have this type of discrete system. We can generate these fractals. We have also fractals in some other kind of system. We have trajectory. We can quantify the chaos through Lyapunov exponent. If Lyapunov exponent is positive, then we say we have a chaotic situation. This is fractional system. In the fractional system, also we have a chaos and fractal. This. And now next, we have this type of study in fractional system. So we have this type, another kind of fractional system, and we can use this. We can find bifurcation diagram. These are also fractals. How to quantify that these pictures are fractal? So we find the fractal dimension. It must be non-integer. So these are self-assembly dimension, Bose-Conti dimension, half-dot dimension, a lot of dimension. So we have non-integer dimension. One of the self-assembly dimension we can define like this. which is we have done in the beginning when we cut and put and we get a portion. So we can find the Cantor set dimension is 0.6, coach curve 1.26, snowflake 1.26, like that. And now last one is we apply this fractal technique to compute a fractal dimension of coastline Australia. This is my highest cited paper, and this is published in scientific report. After that, we have calculated, apply this fractal technique to study the coast length of coastline, fractal dimension of coastline of India. It is also very good journal, published in good journal, Computer and Geoscience. Last is this, we use this technique to compute a Boss County dimension border of Kingdom of Saudi Arabia. So a lot of application, a lot of things behind the fractals and chaos theory using the nonlinear system, but due to time and we cannot go, but Ramanujan also stamp, but fractals also on the stamps. So thank you very much for listening me.
Now the floor is open for the question answer session.
Good morning, sir.
Good morning.
Sir, I'm very happy to see your research. I I'm very happy to see your research, sir. And by seeing your research, I have got so many doubts.
Okay, okay. You ask. If you have doubt,
Not
this is due
one,
to this I am here. Okay. If
not
you have
one,
question, ask. Okay.
not one, but so many. That's why if I don't forget, that's why I have written in my
Okay,
copy.
no problem, no problem.
Sir, first of all, I just want to know how a layman can get the cows, the chaotic
Yes, you
behavior.
see that this book by Devani, a dynamical system by Devani. It is published about 1990, first version, and after that the second, third version. But that is very basic, defined like ABCD. Okay.
Okay,
Once
okay,
you read, then you get automatically a higher references.
okay, okay, okay.
Okay.
Sir, second,
Because if you see the books, if
yes,
you
sir.
read the research paper, maybe many things are missing because they write in very short. But you go the book,
Sir.
yes,
Okay, sir. Second and very, very important question.
yes.
c- How we determine cows?
This I explain.
You explain what can we determine T versus number of variables like X, Y, Z, whatever
I
variable.
say first you define a situation. Okay. It is a phenomena. It is not a object.
Okay, okay.
First you must see the behavior of your trajectories. I have shown the many trajectories. Okay.
Yeah,
So
I've
first
seen.
you find the trajectory and find the Lyapunov exponent. That is simple. Lyapunov exponent means you just say the difference of before point, next point. When two trajectory very close, Lyapunov exponent, and it may be go like this. Means
I got that,
yes,
sir. I got. But question is that
yes.
can we get the cows T versus X, or only we can get
No, no.
X versus Y?
T, X, Y, no problem. You
Yeah.
just find the trajectory of your iteration.
Okay, okay.
Two trajectory, and then you see difference. Okay. When
Oh,
this far away, simple definition is this.
okay,
And
okay.
okay. It is no associated with T, S, Y, Z. Just you find trajectory. How you find your trajectory, that
Yes,
is
sir.
important. Sequence. Simple is sequence, basic sequence you study in your high school. Okay. You
Yes, sir.
write A1, A2, A3, A. Simple this sequence you write, two sequence, and just take the difference. This
Sir,
is the initialization root of the chaos. Okay. Do
sir,
that. Yes.
as far as
Yes.
I have seen your whole research
Yes.
here, only you told about the non-linear part.
Yes.
Can we get for linear same?
No, no. I say chaos exists only if basic condition is non-linearity. Okay. We can
Basic.
generate fractal for anything. Fractal is different theory. Chaos is different theory. Don't confuse like this. Just like a statistic or probability.
Yes.
Okay. Statistic is one part, probability another part, but 99% we teach statistic and probability together.
Yes,
In
sir.
our mind, statistic and probability is a one subject. Same is here. Fractal is one subject, chaos is another
Yeah,
subject.
that's different, sir.
Okay,
Yes.
generally come together. So fractal we can generate for any system. Linear, non-linear, there is no problem. But in the chaotic system, basic condition, first condition is I have written non-linearity.
Yes, sir. Basically,
Okay.
I'm asking that
Yes. Yes.
you all
Yes.
you
You must know difference. Okay.
okay,
First.
okay.
Yes.
And sir, what we yes.
Okay.
Yeah. Any other question we can take? Salman, quick question. Like,
Sir, good afternoon, sir.
Okay. Good.
Very good lecture on this. Actually, I'm working on this one.
Okay.
So I'm an initial learner.
Okay.
So I'm asking you that many of the papers I saw Dr. Anita ma'am and
Yes.
yourself also.
Yes.
So they are using someone using sine function, complex function like sine,
Yes.
logarithmic function, exponential function. So anything, any idea about that? Any suggestion for me that I will use like a function of a that is not sine or cos type. We just mix up all the things.
Yes, you
Yes,
can
yes,
take
yes.
any special function. I
Yes,
have
yes.
done many paper
Okay,
for
okay.
real analysis. You can just use Z and
Okay.
find convergence like her.
Okay, okay.
Okay.
Because in embroidery systems,
I
there are
don't get time. Actually, I
yes,
am
yes.
try to student give an
Okay,
idea,
okay.
but I
Actually,
don't
I'm
have
working
time
on it,
to.
so that's why I
Yes.
just need a suggestion from you to
Yes. Okay.
do something new.
Yes.
Yes, yes, yes.
Yes. No, 10 is actually
Work done.
not go for my suggestion for 10 not go.
Okay, okay,
Okay.
okay. Yes, I will.
In start your convergence, first iteration diverge, you stop. You
Okay.
don't get fractal.
Yes, yes.
Okay.
10, 0. Yeah,
Yes.
yeah. Understood.
You
Understood.
if you so convergence is the problem. I struggle from 10 in far last 20 years, but I don't get any
Actually, I
fractal.
tried for the log function, but ma'am already done in
Yes.
2023. She have a
There
paper.
are a lot of functions.
Yes,
You
yes,
take
yes.
any special function. Okay,
Okay,
no
okay,
problem.
okay. Thank you, sir. Thank you.
Yes. Yes, you can apply this any kind. Yes. Because if you try to stability, you get easily fractal. Otherwise, if non-stable region, no problem. Yes. Ask question. It is good for everyone. Okay.
Sir,
Yes.
in your presentation, I have seen fractal is flowing everywhere. It was very nice.
Yes.
So I have seen you are using ordinary derivative. Why you are not using fractal derivative?
Fractional.
Not fractional is different.
Yes.
Fractal is different.
Yes.
Fractional we are using ordinary
Yes.
measure. Fractal we are using
Yes.
fast dot measure.
Some
My
people
point
used.
is
Yes.
no, sir, that is wrong. Totally
Yes.
wrong concept.
Yes.
My point is why you are not using fractal derivative. You are
Yes,
simply
I
using.
say I have not used because my focus only in discrete dynamical system. Okay.
Okay,
So
okay,
my
okay.
paper mostly based on discrete dynamical system. Very few of them is we have done for discontinuous. We have generated directly fractals. We have generated directly fractal using discrete. This is also very big confusion. Whenever you study the fractals, also we generate by two kind of system when you iterate. One is discrete system, one is continuous system. Continuous system you do directly, but in the discrete system, first you discretize the system and use the approximation. So in the discrete, there is big approximation. So every time due to this, people are changing the iteration scheme. Okay, somebody asked before this question, they why use this? Because due to convergence, they in the discrete form, the function get different form. So they change the scheme and try to converge and generate a fractal. They don't know about the how what is the actual convergence. They don't drive the formula of convergence. So mostly my paper, myself or some other paper have incomplete information because we don't drive the convergence. Just computer give you convergence. Just we don't know mathematics. Okay.
thank you, sir. Thanks for your nice talk.
Okay. Thank
Have
you.
a big round of applause. You can during the lunch time you can take the question. Okay, thank you, sir.
Now I'd like our session chair to felicitate sir with a token of appreciation. Also, yesterday, Professor Anita Toma gave her invited talk on fixed theories. So I would also like our session chair to felicitate her. I request Anita ma'am to please come forward. A big round of applause for her. Also, we have come across a pen drive. If anyone has lost it, they can take it from their technical desk.
Kumar, what's brief introduction about him. So currently, Professor Watts is working in NIT Hamirpur as an associate professor. He was the head of.
First of all, thank you to the organizer, especially thank to the Professor Hemant Nashin to invite me for sharing my views about the my research topic, that is current and the future perspective in the controllability by the fractional system, fractional calculus and fractional system. Then this is the title of my topic. That is, the next one is these are the contents of my topic. That is, first is the introduction of the fractional calculus, and then fixed point theory. Many of the researchers and many of the speakers have already introduced this fixed point theory. I just would like to skip this point. And third one is the controllability. What is the controllability? And final one is that is the controllability of the fractional order system, recent advances, that is perspectives. And final, we would like, if time will permit us, then we will discuss what work is going to be nowadays in this controllability using the fractional system. Then this is the abstract of my talk. Basic abstract of my talk is, we will outline the concept of the controllability and the fractional calculus, and further, and using this fractional system and the controllability. And finally, many of the speakers discuss about the fixed point theory. Using the fixed point theory, that is a convergence and divergence, and we can finally use that fixed point theory and fractional calculus, fractional differentiation in the theory of the controllability, which is very useful in the nowadays in the robotics and the many engineering problem. And just you can see in every day, you can see in earlier days, you see that is our lift system that stops after taking some times, but nowadays it stops immediately. That is the concept using that one, the fractional calculus. This is the main abstract of my theory. That is, first I would like to introduce, that is fractional calculus. As the word the fraction, that is the just a meaning of the fractional, that is a some part, not completely complete part. That is the same meaning is here used in the fractional calculus also. That means what we see often is only a fractional part of what is really it is. And this is the main word from taken, it is from here. Then one, that is the why and in the fractional calculus, that is the brief history of the fractional calculus, brief introduction of the fractional calculus. Why in this ordinary derivative, that is n has to be a positive integer, n belongs to the positive integer. Why this question has been raised by some of the mathematician in the earlier. That is, we also said this negative derivative is the integer derivative is equivalent to the integral number of integral, that because it is the just reverse part of the dot in derivative. The next one is the, in turns out this question has been asked by the L'Hopital in the letter to the Leibniz in 1695. that what he wrote, what would happen if we take n is equal to be 1 by 2 in this ordinary derivative where we have taken earlier, it is n belongs to the positive integer. And in that letter, he wrote that what will happen if n will become the 1 by 2 and another fractional part, then the Leibniz wrote this is an appearance paradox from which one day will draw a useful consequences. That means in 1730, after that, in 1738, the Euler introduced this alpha derivative of x raised to power beta, where alpha beta both are the positive real number. And this is the concept of the gamma function. As we have already aware about the gamma function, that is this fractional derivative is linked with the gamma function. Using the definition of the gamma function, this is the gamma function. Then come to the part of that one is which is the formal generalization of the elementary fact of the fractional calculus, that is the gamma function, because gamma of beta plus 1 is the vector. If it is beta is a positive integer, that is factorial beta, but if it is not a positive integer, then in the term of the another part, then around 1830s, Liouville considered the function that can be written as a series. This is the function. The function can be represented in the terms of the series exponential function, exponential series, and then consider the alpha derivative of that exponential series in the terms of the function. But these definition leads to the controversies. That means these definition leads to the contradiction, because the derivative of a constant functions will become zero, but we consider the fractional derivative that leads to be not become zero. That leads the contradiction, because exponential function, the expansion of this exponential function by using the Taylor series is this one, and by Euler definition, if we consider the derivative of this e raised to power x, it is equal to be this one, which is not equal to be e to power x. That means it means leads the contradiction, by which is the contradiction. Then in 1823, Abels considered the Teutoconn problem, posed his solution in terms of the integral equation. Later on, this problem was considered the first application of the fractional calculus. That is Teutoconn problem. What you can see the Teutoconn problem, that is a one ball fall from any place, that it doesn't matter with the position of the ball, but when it starts from the one point, and then you see that the every ball reach at the same time. That position is the different, and but it reach at the same time. It is the Titokono problem, that is same time. Then in mid of 19th century, Riemann and Liouville introduced the fractional derivative, and this is the definition of given by the Riemann and Liouville, that is fractional derivative. That is this J stands for the fractional integral. First, it introduced by the fractional integral, because using the fractional integral, they introduced the fractional derivative. Then come to the part of the using the Cauchy integral, that is n derivative can be converted into the single integral. Using this application, they can apply this application to the by introduction of the fractional calculus, fractional derivative. The Cauchy formula for the repeated integration compress n times of the function into the single integral. The Riemann-Liouville fractional derivative of order alpha is defined as, this is the definition of the Riemann-Liouville fractional derivative introduced by the Riemann and Liouville, where n is the in 1967. And Capito introduced the Capito fractional derivative by exchanging the order of the derivative and the integral. In earlier one, you can see first the integral, then it is a ordinary. But the Capito changed the order. Then first we consider the derivative and then order of the derivative integral. Then alpha defined by this one. This is the definition. First we consider the integral, then it is a simple consider the ordinary derivative dn, that is ordinary derivative, and then nth integral of that part. This is the relation between the Riemann-Liouville and the Capito fractional derivative. Between these two, this is the relation between the zero initial conditions. And you can see the Hilfer introduced the new definition of the fractional derivative, at the end of the 20th century known as the Hilford fractional derivative. It is this Hilford fraction, this is the definition of the Hilford fractional derivative. Basically, the Hilford fractional derivative is the generalization of both the derivative Riemann-Levelly and the Capito fractional. The particular both will become the particular case of the Hilford fractional derivative. You can see when v is equal to be 0 and this gamma lies between 0 to 1, the Hilford fractional derivative becomes the Riemann-Levelly derivative. And if we consider the alpha v is equal to be 1 and the sigma is same, then it becomes the Capito fractional derivative. It means the Hilford fractional derivative is the generalization part of the both the derivative, both fractional derivative. And this is the basically application of the, these are the basically application of the fractional derivative. In last two decades, the 19th century, Heaviside successfully developed his operational calculus. In 1892, he introduced the idea of fractional calculus in the electric transmission. And these are the basic: increase the speed of the response, decrease the relative speed stability, decrease the element steady state error. I have given the example of the this lift. Earlier days, the lift, when we press the button of the stop or this one, that will take the time to stop up and down. But nowadays, it's immediately stop. That is the basic application of the fractional derivative. And these are the fractional damping applications. And these are the basic main papers or main books of the control theory, image theory, bioengineering, where this fractional derivative are applied. These are the basic results in the different journals in the where they have introduced the application, the different areas: signal processing, economics, electronics, telecommunications. And then come to the part of the fixed point theory. Then many researchers have already taken elaborated this fixed point theory. I just would like to skip this one. Fixed point theory, what is the basic fixed point theory, and two fixed point, many fixed point, infinite, shorter. These are the different uh, fixed point theorems which are to be used to find the controllability and using the fractional calculus. Krasnow-Selsky fixed point theorem. And come to the part of the controllability, that this is the basic, that is, you can't control without being controlled. Then this is the phrase, the you can't control without being the controlled. Then controllability is the fundamental concept of the mathematical control theory. This is the fundamental. The main books on this control theory is the R.A. Kalman theory, given by he wrote a book, that is R.A. Kalman. The controllability is a fundamental concept of the mathematical control theory. So before this, we throw light on the history. That is control brief introduction. That is, control theory is an interdisciplinary branch of engineering and the mathematics that is behavior of the dynamical system to achieve the desired goal. That a control mechanism are widespread in nature. For example, the biological system, the human body, that is blood sugar is to be controlled, and everything that is to be controlled. Then you can live comfortably. Insect and animal population are controlled by very delicately balanced predictor relationship. Several man-made control system and such as missiles and the nuclear reactors, automatic washing machines, all these in these theorems, these mechanism, that is control theory mechanism, is to be used, and otherwise it harms to the our life system. However, whether a system is a natural man-made, they have a common aim is to be control or regulate a particular variable within the certain operating limits. Control mechanism has been seen since the ancient times, that is 2000 year old, that is 2000 BC, where the control of the irregular irrigation system was also well known art. That means the control theory. These are the control theory has gained remarkable impact in the 1769 and 1860s. Scottish scientist James Maxwell published first mathematical description, and 1950 powerful generation. Then the control theory is nowadays being viewed from two perspectives: theoretical foundation, the control engineerings. Then how do I explain control to a layman? How to explain, that is the basic concept, how to explain the controllability to a layman. That means Imagine that we have a toy, robotic toy. You can you have a child in your home. You produce a you give him a car, that is toy car, by remote control. You hand over to the remote to the that one, that is try to use that remote. The car will play either or move in the either side. That is the very example of this control theory, that is measuring the distance of the car from the wall, which decide the call that this is the car. We fix up a sensor on this room one wall, then car can be moved from left and right by using that remote. Then this controllability, thus it's the position axis controllable. If we can move that car from the away from this wall, then control the that sensor is not working, then system is uncontrollable. Similarly, we can explain, but since the car can move only left and right, we do not have any means of the influencing its position. Why? Its position is uncontrollable in the another directions. If we fix up, we would like to see the car should be moved in the another direction also, we have to fix up another sensor in the another direction also. That is, we thus the position y becomes the controllable, and we decide to solve this problem by installing a sensor on the lower wall also. We can then this car can be moved in any other direction by using the two sensors on the two walls. The car can be controllable in the both the directions also. That this is the R.E. Kalman in 1960, controllability, the fundamental concept of the mathematical control theory introduced by the R.E. Kalman. Controllability is the qualitative property of the dynamical control that plays an essential role in developing modern mathematician control theory, finite and infinite dimensional, and ordinary differential. Theory is this the non-linear system represented by evaluation equation. The inclusion system in abstract space lead to the some important conclusion regarding the linear and non-linear system. Many scientists and engineering problem are non-linear, can be elaborated by using this control theory. So study of the control in finite dimension is very, this is the consider an example, very simple example, by using the mathematical, by deriving the mathematical equations and using the control theory, we can explain this state. This is the trajectory path. I would like to find this trajectory path. This endpoint should be 6 instead of 2. That is initial point we have given, that is we choose the final state, that is after 2 minutes or 2 seconds, it should be 6. That is our final desire. But in general, it cannot be go there. It goes to be up to this 2. Then we fix up some another system, that is a control function, to find out the this the ut is the control function. If we introduce this control function in this differential equation, we can find the final state of that desired state, that this system will reach at point 6 after the 2 seconds. It will reach to after applying the control system. Another example, we have taken the water tank, that is kept as a two taps. One is a upper inlet tap and another one is a outlet tap. If outlet tap is a rate of outflow is more than the inflow, then tank will be empty after some times. And but our need is that the level of the water is to be same. So that means we have to fix up the rate. Either we should rate for the both the inlet or outlet should be same, or we can apply some another system. That means both shapes are open and water 2 is getting mixed into the solution of the instantly. The solution, this is the differential equation. This is the differential equation of that system, and the particularly r is equal to be 2v. This is the derivative of that one. We consider this one initially, we have considered this x is equal to be 0.5, and using this initially we would like to get the final state, that is the solution is to be controlled, that is salted water should be same thin. This is the initial when we do not we have not applied any control function, and this is the solution. Any decrease of the concentration of the salted water is going to be decreased. If we apply the control function on this one, this concentration of the one is same. That is how much salt should be mixed with the solution per unit time so that the concentration remains same after t second. Then you can see after t is equal to be 6, the concentration of the salted water will be the same after applying this control function. This is the mathematically we can use here. Ut is the control function, at and bt are the different the given system, and then x is equal to be by using this solutions we can find the system is to be controlled by initial conditions and the final conditions. These are the conditions for the controllability, whether system is to be controlled or not. On the u belongs to the L square L2, and then you can find the continuous conditions. This define the operator C by on using this control function. C is bounded linear operator, range of C is subspace of Rn, and range C is called the reachable set of the system. Then controllability gramming, that is main condition. If you see the physical system is to be controlled, or you can see by using the this gramming matrix, you can see mathematically whether system is to be controlled or not to be controlled. Controllability gramming matrix. This is a controllability gramming matrix defined by this one. And when this gramming matrix is this one, rank of, we can find the rank of this gramming matrix. If this is the third example by considering the tank 1 and tank 2, u is the control functions and alpha is the outlet, and the third one is the beta is the outlet. Then we can define the mathematically for this, and we can consider it is a linear system by using the matrix theory. We can try to solve it, and the rank of this b colon augmented matrix is 2. Then as per the definition of the Gramin matrix, if it is equal to be this one, that is tank model 1 is controllable. Then this is the by definition of the Gramin matrix. The tank is controllable. And the another system, this is the another system, another physical problem in which we consider we do not have any inlet in the first tank. We just have the outlet from the first tank and inlet in the second tank, that is U. If that U is the control functions. If we do not want to this control fix up at the control function, the concentration in the second water may be decrease or maybe increase if it is that is depends on the concentration of the water in the first tank. This is the mathematical model method that is tank. If you can see the rank of this one is 1, that means this rank is not equal to be the rank of the original matrix A. So this system is not controllable. The system is not controllable. That is the basic definition of the controllability. We can check the system mathematically as well as the physically where the system they consider the spring mass system, unit mass with the spring. Again, we can derive the mathematically model and we can check the that one is then B, and same is the system is not controllable because the that condition, mathematical condition, is not fulfilled by this condition. Then we have some different type of the controllability: exact controllability, approximate controllability, and the third one is this exact controllability. We have the final state, the our we can reach the exactly from the final initial state to the final state. This is an example: automatic cruise control, that is nowadays we can see in our car, that is cruise control. That is a basic example, basic application of the control theory, that is cruise control nowadays is applicable to in our vehicles, so that we can feel the comfortable. The speed of the vehicle is controlled by the adjusting the throttle opening. The dynamics of the vehicle speed can be represented in the first order linear differential equation. M is the mass and this is the control function by throttle that opening, this one. The exact controllability, let us define the well-defined control function with this one. And A represent the specific throttle opening setting. And this cruise control scenario, goal of the exact controllability is the preciously set of the opening, and realistic example is how to exact controllability is implemented to everyday automatic system to provide convenience and more comfortable over. Next one is approximate controllability. That is arbitrary initial state vector may be steered close to the final state, though not exact to the final state, that is very close to the final state. This is an example temperature control in a room that is not exactly the at the same point, that is very near to be that final state. That means the approximate controllability is to be used in that system. That is a rate of change of the room temperature. K, these are the basic Newton law of cooling. Using this Newton law of cooling, we have fixed up the control function. That after fix up the control function, this temperature is near to be our requirement. And now let us define the control function ut. It represents the heating effect, that is H if it's too cold, C if it is too hot, and it is close to our desired temperature. And these are the different notation for that one. The approximate controllability means using the control function ut, the influence of the room towards our desired comfort level, not exactly that exact one, that one. The third one is the trajectory controllability. We have a fix the path, our final goal, any final desire things is along that path. That means the trajectory controllability, prescribed path. That is, this is an example, but mathematically we can see the projectile such as the ball launches into the air, the trajectory dx upon these are mathematical model using those differential equations. And projectile motion is that one is x and y horizontal and vertical position of the projectile system, t is the time, and v naught is the initial velocity. These are the different notations for those mathematical models. And this is the control function which are to be like to be defined for applicable to here. Basic definition: theta represents the different launches angles during the specific time intervals. Goal of trajectory controllability is to precise control and trajectory of the projectile by adjusting launch angle of the different level. Just this trajectory path, trajectory controllability is used to the missiles. When we in the defense system, it is very important. Our defense system, the scenario, the well-defined control functions allows the trajectory controllability, enabling adjustment to the launch angle of the specific interval achieve desired trajectory shapes. Third one is that final is the null controllability. Final is the total controllability. Null controllability, any state vector may be steered to be null vectors. The null controllability of the draining tank after times imagine you can have a tank filled with water. There is a tap at the bottom which is outlet. You can see after time sometimes this tank will be over. This is a type of the controllability. Next. भाई ये तो चलता ही नहीं. This is the mathematical model of that null controllability. You can see. And total controllability, that is initial state to the arbitrary state in each interval. Earlier you can see in exact controllability, approximate controllability, that is at the final point, our desired point at the after some times. But in this total controllability, that final state is in each interval. That means the total controllability. These are the basic examples of the total controllability. You can see over here. And these are the some applications where this controllability function is are to be used. And finally we have the controllability using the fractional system, fractional order system, recent advances and a perspective of this controllability by using the fractional order system. Controllability fractional represents the fascinating and evolving domain with the broader field of control theory functions. Over the past decades, you can find these definition, these applications of the controllability with this. Kilbas initiated foundation work by advancing theory of the fractional calculus, paying this one. These Patras significant influence analysis and control functions, and this these are the basic some given. I just to introduce the controllability control design for the fractional system. These are the designs for using the control functions. stability and the robustness of the control, optimal control and the optimization, application in science and engineering, hybrid system and fractional system. I just to hide all the application, all the work which we had used by these control functions, then we can using this final, we have taken some problem, a one problem using the infinite dimensional. If it time permit, we can give this one. Otherwise, we can. This is our work in infinite dimensional, sir. Sir, please.
Shortage of work time,
Okay,
sir. Yeah.
no problem.
So you can sum up anything.
See, this is sum up. That is finally would like to explore this in the infinite dimensionals, and just like to conclusion, go to the conclusion. Different definitions, and basically instantaneous, non-instantaneous, and mild solution. That is the basically our aim is to fractional calculus is our basically aim how to solve the fractional system. First, try to convert that fractional system into the linear system, non-linear system into the linear system. First, find the solution of that linear system using the fixed point theory, and then applicable to the different systems. That solution is to be comply with the non-linear system. That is the basic theory which are to be used over here. That is main conclusion of this one. Approximate controllability, and these are the different theorems which are to be used, and these are the basic results one and result two. This is the work which I would like to share, that is which we did using the control functions and the fractional calculus. That is the sufficient condition for the existence of the mild solution and the approximate controllability for a class of non-densely Hilbert neutral differential system. Non-locally conditions have been investigated in this problem by using the fixed point techniques, semi-group theory of abstract, fractional calculus. We proved the main results. In future, we can extend this one, and these are the some references of this control theory and the other ones. Thank you for your attention.
Thank you so much. Due to the time shortage, I'm not taking any question. You can discuss in the lunch during the lunch time. So we can honor the Professor Ramesh words.
Now I request sir to please felicitate sir with the token of appreciation. A big round of applause for sir.
So, very good afternoon to all. So, first of all, I would like to thank the organizers for giving me the opportunity to present my work here in this conference. So, today I will be talking on the numerical approach to matrix sign function and just an overview and the recent developments. So here is the brief outline of the presentation. So first we will see what are matrix functions, and then the special case, that is matrix sign function, we will describe. Then what are the numerical different approaches to compute the matrix sign function, and then what are the recent developments and applications of matrix sign function, and the last one is the development of new iterative technique to compute matrix sign function, and then the conclusion and some future directions for the young scholars. So let us first see what do we mean by matrix function. So basically matrix function can have several different meanings. Like we have functions which map a matrix to scalar quantities such as determinant of a matrix, trace of a matrix, right? So this is the first category. Second is we have certain functions which perform element wise operations, like in MATLAB or any other computer algebra system. We perform sine of a, cos of a, so they perform the operations element wise. And the third one is we have functions which map a matrix to another matrix, like we calculate the transpose of a matrix or adjoint of a matrix, right? So these are the basic notions of some matrix functions that we already know. So now we are basically interested here in the definition where we are taking some scalar function and a matrix, and we specify the function f of a from Cn by n to Cn by n map. And the common examples are like matrix square root, second one is matrix inverse, and the third one is matrix exponential. So these are the common examples of some matrix functions. So now the study of matrix functions was initiated in Calais 1815 8 memoir, where he studied the calculation of square root of 2 by 2 and 3 by 3 matrices, and then he later revisited these cases in 1872. So basically the research on matrix function that involves matrix theory, numerical analysis, approximation theory, and development of new algorithms. So this is the formal definition of function of a matrix. Say this is the definition by Jordan canonical form. So we have a function f which is defined on the spectrum of the matrix A, which is square matrix having complex entries, and then you write down the A as Jordan canonical form. A is equal to P J P inverse. So this is the JCF of A, and then we define f of a to be given by equation number 1. Here you can see that j1, j2, jr, these are the Jordan blocks of different sizes corresponding to different eigenvalues, lambda 1, lambda 2 up to lambda r. And then similarly you can define f of jk given by equation number 2. So this is the formal definition of a function of a matrix. So you can apply any function, you consider any function and you take any square matrix and just apply the definition, you will have the answer, right? So in order to understand this definition better, I have included one example of 2 cross 2 matrix. So next example is we consider this 2 cross 2 matrix. A is any 2 cross 2 matrix I have considered here, and you consider one function fz is equal to z square, right? So now let us compute f of a. We know that f of a will be equal to a square, and then we will verify whether the answer of a square is coming to be same by this definition or not, right? So what we do, we first write down the Jordan canonical form of this matrix. You are given 2 cross 2 matrix. We know how to write down the Jordan canonical form. P inverse. What is P? P is the set of all eigenvectors, right? The columns are set of eigenvectors. So I have just calculated these eigenvectors. P is your minus 5 plus iota 13 and 1 comma 0, right? And now j, you have eigenvalues on the diagonal minus 4 and 1 plus iota, right? So when you multiply these, you will have a, right? Now your j1 is your first Jordan block, that is minus 4, that is of order 1 cross 1, and j2, that is your second Jordan block, right? So that is having entry 1 plus iota. So now you can calculate f of j1. So that will be minus 4 square, that is 16. And then you can calculate f of 1 plus iota. So 1 plus iota square, that will give you 2 iota. So you apply now the same definition f of a, that is equal to p inverse. So you can see that you are getting this 2 iota comma 0, and the second column is minus 6 plus 2 iota comma 16. So this is how we can calculate the function of a matrix using this definition of Jordan canonical form. And now the same can be verified if you take a square, so you will get the same answer, right? So this definition holds good for any square matrices and any kind of scalar functions, right? So now we are considering here some special case of matrix function, although there are many matrix functions, but we are particularly interested in matrix sign function. So matrix sign function is basically uh, introduced by J.D. Roberts in 1971 as a tool for model reduction for calculating different equations. So we first try to connect this matrix sign function to the scalar case. Let us see what is the scalar case. So everybody knows that for scalar sign function, what we do, we consider any complex number. If the real part of that complex number is positive, then we say that the sign of z is 1, and if real part of z is negative, then sign of z is -1. So this is the definition everybody knows. And we also represent sign of z as z by z square under root. So you can also visualize sign z like this, right? So now what we do, we generalize this definition sign of a given by equation number 9. So here you can see that we are having uh, principal square root of the matrix. So this is the just the idea that how we can extend our scalar cases to the matrix cases. So scalar sign function is extended here to the matrix sign function. So now this is the informal way, or you can say this is the just simple way to extend the scalar case to the matrix case. But now let us see how our previous definition of Jordan canonical form, how that definition is helpful to find out the matrix sign function, right? So this is the, again, I am applying the same definition here, but we have studied for matrix functions. Apply the same definition to calculate matrix sign function. So we get this expression given by equation number 10. So it says that suppose you have any complex matrix, any square matrix having no eigenvalues on the imaginary axis, such that sign of A is defined, that means A is your non-singular. Now if A is your Jordan canonical form such that J is equal to diagonal of J1 and J2, or J minus or J plus, where J minus is the Jordan block corresponding to the left half plane and J plus is the Jordan block corresponding to the right half plane. So this is how you can compute sign of A given by the equation number 10. So this is the same definition, right? So you will get the same answer whether you apply the simple definition that is given on the last line or you apply this JCF definition. So we are getting the sign of a matrix, right? So now again I have included one example to calculate how the sign of a matrix will look like. So again you consider the same matrix, 2 cross 2 matrix. Now you apply the same definition which I have considered with the help of Jordan canonical form. So again you have eigenvalues lambda 1 and lambda 2. So lambda 1 is your -4, so real part is less than 0, and lambda 2 is your 1 plus iota, so real part is 1, that is greater than 0, right? So you can apply the sign definition, because this is the condition that you can apply the sign definition if and only if your A has eigenvalues not lying on the imaginary axis. So one of the eigenvalues is -4 and the other is 1 plus iota. So both eigenvalues, they are not lying on the imaginary axis. So the sign function is defined in this case. So now you apply the definition. You first write down A is equal to P inverse. This is the same matrix that I have considered before. Now so this is the definition sign of A, that is P inverse. So I have replaced J by this matrix here. So you just plug in the entries. P is the same matrix. IP, that is the identity matrix of order P. IN minus P, that is the identity matrix of order N minus P. If you multiply all these three matrices, you will have sign of A, that is given by equation number 13. So this is how we can calculate the sign of a matrix, any square matrix, right? So this is the one example I have included to just to show that how the sign of a matrix will look like, right? Now we are interested in studying the various different properties of sign of a matrix, like what type of properties it is satisfying. So the first property is that it is always a involutory matrix. If I give the notation sign of A is equal to S, so S square will always be equal to I. That means S is a involutory matrix, right? So the inverse is equal to the transpose of this matrix. So the proof is very simple. Just you can take S is equal to sign of A from the definition, just you multiply S square. So when you multiply S square, you will get that we are getting the identity matrix of order n. So this will shows that the theoretical proof, simple proof, one line proof that shows that S is the involutory matrix. So this is the first property, that is it is satisfying by the matrix sign function. Second one is that sign of A, this is a special matrix, and an interesting property is that this is always diagonalizable with eigenvalues plus minus 1, right? So you can again verify this property. Simple proof is very simple. So S is equal to P times this matrix into P inverse. So if you multiply P inverse SP, so what is the definition of a diagonalizable matrix? So if we say that the matrix is diagonalizable, then it is similar to a diagonal matrix. It should be similar to a diagonal matrix. So if you see that P inverse SP, so what you are getting? You are getting a diagonal matrix. There is no non-zero entry on the non-diagonal terms. So we say that this is a diagonalizable matrix. Again, the eigenvalues are plus minus 1, because minus IP, what are the entries? Minus 1, and so on. And on in minus p, what are the entries? 1, 1, 1. So whatever the entries on the diagonal we have, those are the eigenvalues. So this is the second property, that it is always diagonalizable with the eigenvalues plus minus 1. So this is the second property defined by the matrix sign function. Now this is the same definition, just I have shown that this is also satisfying, but the two properties I have stated here, that S square is equal to Y, and the S is diagonalizable with eigenvalues plus minus 1. So these both properties are satisfied in the previous example also. This is just the verification of that. So some more properties, they are satisfied by the sign function. So first property is that this is commuting with the original matrix. Second one is, if A is real, then the sign matrix is also real. And the third one is I plus S by 2. I is the identity matrix, and as this S is the sign matrix. So I plus S by 2 and I minus S by 2. These are the two matrices. So basically they will be the projections, right, on the left of plane and the right of plane respectively. So these are another three properties which are enjoyed by the sign matrix sign function, right? So now uh, uh, we turn towards numerical approach. Why? Because with the help of some definition, analytical definition, or by applying some analytical tools or analytical methods, there is one method known as Schur's method, which is used to compute the matrix sign function. But those methods are highly computationally complex, or you can say the computation complexity is very high. So in order to reduce the computation complexity, or to reduce the CPU time, what we need to do, we need to take the help of numerical methods. So what we do, we turn towards the numerical method to compute the matrix sign function. And the idea is very simple, like I have included here uh, the best known method for computing the scalar nonlinear equation, roots of nonlinear equation, that is the Newton's method. Everyone is familiar with this method. This is the method known as Newton's method. So now when you apply this method to the equation x square minus 1 is equal to 0, because ultimately we want plus minus 1, those are the eigenvalues of the sign matrix. So when you apply the Newton's method on this equation, so what you get, you get equation number 17. So this is the Newton's method for computing matrix sign function. And the beauty is that the order of convergence is same. Order of convergence will be 2 in this case also. Like in the scalar case, the order of convergence of Newton's method is 2. Similarly, in this case, the order of convergence will be 2. And the initial guess will be equal to A. So wherever from you start with the original matrix A, the convergence is guaranteed, and the order of convergence will be 2. So this is the uh, numerical approach, first simple numerical approach. And now similarly, when you want to avoid the inverses, so when you place yk by xk inverse by some other variable, say yk, so what you get the inverse Newton's method, right? So the equation number 19, this is the inverse Newton's method to compute the matrix sign function. Similarly, when you apply this method two times, we get doubles Newton's method, right? So this is the equation number 19, right? So this is how there are many simple ideas with the help of which you can generate the new methods to compute matrix sign function. Just I have given you just the overview that how Newton's method, how double Newton method, how inverse method, they are used to compute the matrix sign function. This is just the basics of that, right? So now the next idea, this is also one of the most prominent idea in matrix sign function, that is the paired iterations. How this is helpful in calculating matrix sign function. This is the third category I am going to show you. So again, you just start with the very basic, you start with the very definition, sin z is equal to z by z square under root, right? Now, in the denominator, what you do, you add and subtract 1, right? So you will have the factor 1 minus z square. Now you take 1 minus z square to be another variable, let us say zeta, right? So zeta is equal to 1 minus z square. Now you see that I will approximate 1 by 1 minus zeta raised to the power of half with the help of paired approximation, which is given by p by q of order, where p is a polynomial of order r and q is a polynomial of order s, right? So with the help of paired approximation, we are going to get a new family that is given by 24, and the order of convergence in this case will be r plus s plus 1. So this is the paired approximation family, or you can say paired iterations, with the help of which we can compute the matrix sign function. Now there are some questions here, that for what values of r and s we can obtain various different methods. Secondly, what can be said about the convergence of the pairs family for different values of r and s? So these are the two main questions that we need to address here, right? Because when you vary r and s, you will have different families, or you can have different methods, and convergence is also affected when you vary r and s. So r and s, they are playing the major roles in creating the new iterative methods, and that is in the case of paired iteration family, right? So like I'm just showing you the three particular cases. Like for r is equal to 1, s is equal to 0, in the paired iteration family, you are going to get the Newton-Schulz method, right? So this is the first method that we are going to get from the paired iteration family given by equation number 25. Again, the order of convergence of this method is 2. Like Newton's method has order 2, and Newton-Schulz also has order 2. Now similarly, when you take r is equal to 1, s is equal to 1, you will get Hallis method, right? This is the Hallis method, which is going to converge to a matrix sign function, and the order of convergence is 3. This is a cubically convergent method. And again, the initial guess, you start with the original matrix A, you are going to get the iterations which are ultimately converging to matrix sign function, and the order of convergence is 3 in this case. So this is the table I have just shown you to give the just glimpse that how the methods of paired iteration looks like for different values of r, for different values of s, how one can generate variety of methods, infinite methods you can generate with the help of this paired iteration family, which are going to give you the matrix sign function, right? So the I have highlighted few methods here in red color. You can say for r is equal to 0, s is equal to 1, this is the Newton's method. For r is equal to 1, s is equal to 0, this is the Newton-Schulz method. For r is equal to 1, s is equal to 1, this is the Hallis method. And for r is equal to 1, s is equal to 2, this is the double Newton's method. And the order of convergence is r plus s plus 1, right? You add r and s and you add 1 to that. So that is the order of convergence. So this is how this table will show you that how one can generate infinitely many new iterative methods with the help of paired iteration family to compute the matrix sign function, right? So this is the basic idea, and this is very well-known family to create the new methods, right? Now This is the convergence regarding paid iteration. So the whenever you develop any new method, so the question comes in mind that whether the iterations are going to converge or not. Second question comes in our mind that if the iterations are going to converge to the original solution, then what will be the rate of convergence, right? So the both answers are given here in this theorem. The theorem says that if A has no purely imaginary eigenvalues, then the paid iteration family that is definitely going to converge to the solution with the order of convergence R plus S plus 1. And we have included two special results here that says when R is equal to S minus 1 and R is equal to S, you are going to get the globally convergent methods. That is the one achievement. And second is when R is greater than equal to S plus 1, the methods will be locally convergent. And obviously we are primarily more interested in creating the globally convergent methods that from wherever we want to start, just we want the solution, because locally convergent method, they have certain disadvantages. Like in case of Newton's method, you just say that if the initial gas is sufficiently close to the root, only then the method converges. But how sufficiently close, we do not know. But for the case of globally convergence, we say that if you start from the initial matrix A, and if these conditions are satisfied for given values of R and S, the iterations are definitely going to converge to the final solution with the given order of convergence. So that is the meaning of global convergence here, right? So there are some recent developments in this field. So in 2015, Sohili et al., they have proposed some fast numerical methods to compute the matrix sign function given by equation number 28. So they have applied the above four-step iterative algorithm to the nonlinear equation x square minus 1 is equal to 0. And further, they have investigated this method to compute the solution of system of Ito-stochastic differential equation. So these methods are ultimately helpful in calculating the solutions of differential equations also. So this is one of the advantage. Similarly, in 2017, Corredora et al., they have also proposed one extension of Chebyshev-Halley family to find out the solution of this matrix sign function. And then in 2019, they have obtained a slightly different technique. They have not used any nonlinear solver. So they have computed this iteration scheme 29, with the help of which they have computed matrix sign function. And in this paper, they have also included that how to find out the solution of Yang-Baxter-like equation. What is Yang-Baxter-like equation? That is given by this AX is equal to XAX. How to find out the solution of this equation, right? So if you see that I have included one result, that theorem says that if S is your sign of A, then A times I plus S by 2 and A times I minus S by 2. Here these both are the solutions of this Yang-Baxter like equation, and this type of equation is very familiar, and we come across this equation in different fields like knot theory and quantum group theory, right? So they have included this equation in their paper to show the significance of matrix sign function. Similarly, in 2022, for Turchi, they have also used the technique of Adamian decomposition method to compute the matrix sign functions. So there is basically a significant ongoing research aimed at efficiency, computation cost, number of iterations to reduce the computation complexity, and in order to find out the matrix sign function. So this is a very interesting research area. Nowadays, many papers are being published in this research area related to the control theory, how the matrix sign functions, they can be implemented in control theory, differential equations, stochastic differential equations, etc. Right? So these are the different areas in which one can work. This is the motivation to study matrix sign function. So we can have few applications in spectrum splitting, in solving matrix equations, control theory, computing invariant spaces, etc. So I have included a few examples just to go through. First one is application in spectrum splitting. Second one is application in stability analysis of control systems. Third one is application in stochastic differential equations, and the last one is application in computing invariant subspaces, right? So the due to time limitation, I'm not going to explain all these, right? But they have different applications in different fields, so one can use the idea of matrix sign functions in all these areas. Just I have used in three different areas, like in computing invariant spaces and this stability of analysis of control systems. But the third one, this is still open, applications in stochastic differential equations. I have not used the idea in this areas till now. So the when it comes to the significance of a novel iterative family, so we have two major challenges. First one is, whenever you design a new method, that method should not be a member of paid iteration family. That is the first challenge. Or that should not be reciprocal of any paid iterative family. That is the first challenge. Second one should be that the minimum cost should be minimum and the convergence should be global. So these two ideas we keep in mind while designing the new iterative methods to compute matrix sign function, right? So keeping these two things in mind, we have so we can see that we have started with this iteration formula number 34. So originally it is going to converge with the order of convergence 6, but this method will result to a method which already belongs to a paid family. So this is not a new contribution. So you can just have the little bit modification in this formula by adding some factors in the numerator and denominator given by equation number 35, and you can just write down the matrix formulation of 35 given by 36. So one can easily check that this is not a member which belongs to the paid family, right? Because paid family includes member of certain orders. So this is not a member which is belonging to the paid family. And then you can see that if we take xk factor common from this equation number 36 in the second bracket, so you can see that we can eventually decrease the number of matrix multiplication. So this has 5 matrix multiplications, because whenever you design a new method, so the order of convergence should be high and the number of matrix multiplications should be less, right? Yes. So this is the efficiency challenge that is computed with the help of formula given by Trop, p raised to the power 1 by c. So where p is the order of convergence and c is the total computation cost. Next, we can validate the global convergence through the idea of basins of attraction. That just the Dr. Sajid in the previous lecture, he has shown the basics of this, how these basins are helpful in calculating the convergence analysis of certain iteration schemes. So the given proposed family, if says that it is convergent to the matrix sign function with the order convergence 6. So I'm just skipping the proof. So this is the proof of the theorem that it is convergent and converging with the rate of convergence 6. And third one is it is asymptotically stable. So one example we have added to validate the results. So this is the table. We have included various matrices of different orders, 50 cross 50, 100 cross 100, and so on, to calculate the different number of iterations and CPU time, right? So first column is related to the Newton's method, second one is Halley's method, third one is paid approximation for R is equal to 1 and S is equal to 4, and next one is proposed method, and the last column is accelerated proposed method, that is using the scaling technique. So we can see that in the second last column, the mean number of iterations is coming out to be 6, that is comparatively less than the existing techniques. And the last column, that is the accelerated proposed method, the mean number of iterations is 5.1. Similarly, this is the table related to the comparison of CPU time for different methods. So this is the conclusion. The study underscores the importance of various iterative methods and algorithms designed to efficiently compute the matrix sign functions. So whatever method we have studied to solve the nonlinear equations in the scalar case, we can definitely try those methods to extend to the matrix cases and to compute the matrix sign functions. This is one advantage, but obviously not all methods can be extended. We have to see whether they belong to paired family or not, right? And for numerical testing, we can consider the different matrices of different signs for computing matrix sign functions. And the result shows that the proposed method perform better than the existing techniques in terms of iterations and CPU time. So this is our recent some of our papers related to the matrix sign functions. We have just started research in this area a few years back, 2 3 years just we have spent on this, right? So this is the publications we have done in matrix and functions with the help of our students, and these are the references. Thank you very much.
Okay, thank you very much. So if there is any question, please, you are free to ask me. If there is no question, then we can finally thank you very much.
Thank you all for your kind cooperation. It was an enlightening experience to listen all of your insightful discussions. Now, it's time for lunch, which is being served in AB 325. After the lunch, we will begin with our parallel sessions. So I request everyone to please be back in your seats by then. Thank you again for attending the sessions. And even I would like session chair to please felicitate our invited speaker. I request Munish Kansal sir to please come. A big round of applause for sir. Also, the parallel sessions which were going to be held in AB 530 before is now being scheduled to AB 316, and the session which was in AB 529 is shifted to 530. I repeat. I repeat. I repeat, the sessions which were going to be held in AB 530 is now scheduled to AB 316, and AB 529 is shifted to 530. And the, and the lunch is being served in AB 325. Shit. अच्छा फोटो फिर मेरा मुंह खुला ना हो मैं फिर